Most people think the most hostile world in our solar system must be the one closest to the Sun. It seems like an obvious conclusion. Mercury endures temperatures hot enough to melt lead during its endless days. Venus hides beneath clouds where the pressure could crush a submarine and the heat can soften metal. These are the planets that usually come to mind when we picture places beyond human survival. Yet astronomy has a way of rewarding the questions we never thought to ask. Far beyond Saturn, beyond the pale rings of Uranus, nearly 5 billion kilometers from the warmth of the Sun, another world circles in almost permanent twilight. Neptune receives less than 1,000th of the sunlight that reaches Earth. By every simple expectation it should be quiet, cold, almost motionless, a frozen giant drifting peacefully through the darkness. Instead, it is one of the most violent planets we've ever observed. Its atmosphere contains winds that race faster than the speed of sound on Earth. Storms the size of entire continents appear and disappear without warning. Towering clouds rise through layers of methane ice. Deep beneath the visible atmosphere, something unseen continues to release enormous amounts of energy, keeping the entire planet unexpectedly alive despite its extraordinary distance from the Sun. That presents a curious paradox. The farther a planet travels from the Sun, the less energy it receives. Logic suggests that weather should gradually weaken as sunlight fades. Earth possesses active oceans and changing skies because the Sun constantly pours energy into its atmosphere. Mars, receiving less sunlight, is colder and quieter. Beyond Jupiter and Saturn, one might expect this trend to continue until the outermost planets become little more than frozen spheres suspended in silence. Neptune refuses to follow that pattern. The sunlight reaching its cloud tops is so faint that noon there resembles twilight on Earth. Yet its atmosphere is anything but calm. Something hidden beneath those blue clouds appears to be driving the entire planet from within, as though Neptune carries its own private source of weather. Where does that energy come from? That question has occupied planetary scientists for decades. It is not merely about understanding one distant planet. It touches on one of the deeper challenges in astronomy. We are learning that planets are not passive objects simply warmed by their stars. They're evolving worlds with histories, internal engines, and complex interactions that can continue for billions of years after their formation. Neptune may be one of the finest examples of that truth. Ironically, the planet is also one of the least explored. Humanity has landed spacecraft on the Moon. We've driven robotic laboratories across Mars. We've descended through the atmosphere of Saturn's moon Titan and flown repeatedly past Jupiter's icy satellites. Yet Neptune has been visited only once. In August 1989, the spacecraft Voyager 2 swept past the planet after a journey lasting more than a decade. It spent only a few hours close enough to reveal the details of this distant world before continuing into interstellar space. Nearly everything we know about Neptune up close comes from those brief hours of observation, combined with decades of increasingly sophisticated measurements from telescopes here on Earth and in orbit above it. Sometimes science advances not through long conversations, but through remarkably short encounters. Those fleeting images transformed Neptune from a tiny blue dot into a dynamic world of astonishing complexity. Instead of finding an icy sphere asleep in the darkness, Voyager revealed gigantic storms, brilliant clouds, faint rings, mysterious moons, and atmospheric motions unlike anything scientists had expected. Rather than solving Neptune's mysteries, the mission multiplied them. Every answer seemed to uncover another layer of uncertainty. Why does Neptune radiate roughly twice as much energy as it absorbs from the distant Sun? Why are its winds among the fastest measured anywhere in the solar system? Why is its magnetic field tilted so dramatically away from its axis of rotation? Why do enormous dark storms appear, disappear, and migrate across the atmosphere over only a few years? And why does Triton, its largest moon, travel backward around the planet, suggesting a violent history unlike that of almost every other large moon we know? These questions are connected in ways that are not immediately obvious. A storm cannot exist without energy. Energy cannot emerge without a source. A magnetic field reveals something hidden deep inside a planet. A captured moon hints at ancient gravitational encounters that may have reshaped an entire planetary system. Piece by piece, Neptune begins to resemble less a simple gas giant and more an intricate machine whose visible clouds are only the surface expression of processes unfolding thousands of kilometers below. There is another reason Neptune deserves our attention. As astronomers discover planets orbiting distant stars, they have found that worlds similar in size to Neptune appear to be among the most common planets in our galaxy. Curiously, our own solar system contains only two ice giants, Uranus and Neptune, while many other planetary systems seem to possess entire populations of them. Understanding Neptune, therefore, means understanding not merely one remote world, but perhaps one of the most common kinds of planets in the universe. Its atmosphere becomes a laboratory. Its storms become experiments conducted by nature over billions of years. Its hidden interior becomes a window into planetary evolution itself. The farther we look into space, the more frequently we encounter planets that resemble Neptune far more than they resemble Earth. Yet the example closest to home remains surprisingly mysterious. Perhaps that is the greatest irony of all. We have mapped distant galaxies containing hundreds of billions of stars. We have detected planets orbiting suns hundreds of light years away. We have observed the faint glow of the early universe itself. And yet one of the solar system's own major planets still guards secrets that no telescope alone can fully reveal. The deeper we investigate Neptune, the more it begins to challenge some of our simplest assumptions about how planets work. Distance does not necessarily mean stillness. Cold does not always mean inactivity. Darkness does not always mean silence. Some worlds carry their own storms within them. To understand why Neptune has become perhaps the most hostile world in the solar system, we must first understand the assumptions that once made astronomers believe it should have been one of the calmest. That journey begins with a familiar picture of our planetary neighbourhood and the quiet expectations that Neptune would ultimately overturn. Long before anyone knew Neptune existed, the solar system seemed comfortingly complete. For thousands of years, humanity's planetary family ended with Saturn. Beyond its pale golden glow stretched only the fixed stars, silent and seemingly eternal. The planets were wandering lights moving against that distant backdrop, each one following patterns that gradually yielded to careful observation. As telescopes improved, those patterns became clearer, reinforcing the comforting idea that the solar system was an orderly place governed by predictable laws. Even after the discovery of Uranus in 1781, that sense of order remained. Uranus doubled the known size of the solar system almost overnight. It was a remarkable revelation, but not a disruptive one. Here was another giant planet moving quietly around the Sun on a vast orbit. It appeared cold, distant, and serene. Astronomers naturally assumed that any worlds lying even farther from the Sun would simply continue this trend. Greater distance meant less sunlight. Less sunlight meant less energy. Less energy meant calmer atmospheres and slower change. It was an elegant expectation because it matched everyday experience. On Earth, nearly all weather begins with sunlight. The sun warms the oceans, heats the land, drives evaporation, and creates differences in temperature and pressure. Warm air rises, cooler air sinks. Winds carry energy from one region to another. Clouds gather, storms develop, and rain eventually returns water to the surface before the cycle begins again. Remove the sun from that system and Earth's weather would gradually fade into stillness. The oceans would freeze, clouds would disappear, winds would weaken until the atmosphere itself settled into a quiet equilibrium. This relationship between sunlight and weather appears throughout the solar system. Mercury, almost without an atmosphere, experiences no meaningful weather at all. Mars receives less solar energy than Earth, and although it produces immense dust storms, they occur within a much thinner atmosphere. Jupiter and Saturn, despite their enormous sizes, receive only a fraction of Earth's sunlight, yet they still possess dynamic atmospheres because they generate substantial internal heat left over from their formation. That last detail would eventually become very important. A planet's weather is not determined solely by the energy it receives from its star. It also depends on how much energy emerges from within. This idea seems almost counterintuitive at first. Planets appear solid and permanent. We tend to imagine them as objects that simply absorb sunlight during the day and cool during the night. In reality, every planet carries a history deep beneath its visible surface. Some continue releasing heat accumulated during their birth billions of years ago. Others generate additional energy through the slow compression of their interiors or through the separation of heavier materials sinking toward their centers. A planet, in other words, is not merely illuminated from the outside. It may also glow ever so slightly from within. Even before reaching Neptune, astronomers had already begun to appreciate this complexity. Jupiter radiates significantly more energy than it receives from the Sun. Saturn does the same. Their magnificent cloud bands, immense storms, and powerful jet streams are sustained not only by distant sunlight, but also by internal heat steadily escaping into space. The famous Great Red Spot on Jupiter is only one visible expression of energy rising from far below the cloud tops. If Jupiter and Saturn could remain active despite their great distances from the Sun, perhaps Neptune might as well. Yet there was another reason to expect Neptune to be different. Unlike Jupiter and Saturn, Neptune belongs to a smaller family known as the ice giants. Although the name suggests worlds made primarily of frozen material, the reality is more subtle. Deep inside Neptune are enormous quantities of water, ammonia, and methane existing under pressures so extreme that they no longer behave as familiar liquid solids or gases. Instead, they occupy exotic states of matter that cannot naturally exist anywhere on Earth's surface. The distinction between gas giants and ice giants reflects their composition rather than their temperature. Jupiter and Saturn are dominated by hydrogen and helium. Neptune and Uranus contain far greater proportions of heavier volatile compounds mixed with rock and metal. This difference affects nearly everything about their interiors, their magnetic fields, their evolution, and ultimately their atmospheres. At first glance, however, Uranus and Neptune appear almost like twins. Each has a deep blue appearance created by methane absorbing red wavelengths of sunlight, while reflecting blue light back into space. Each possesses faint rings. Each rotates rapidly, completing a day in roughly 17 hours despite taking decades to orbit the Sun. Each experiences temperatures approaching negative 200 degrees Celsius in its upper atmosphere. From a distance, they seem almost interchangeable. That similarity led astronomers to expect similar behavior. Instead, the closer they looked, the more striking the differences became. Uranus is comparatively subdued. Although modern observations have revealed seasonal storms and unexpected atmospheric activity, it generally appears less energetic than Neptune. Neptune, by contrast, displays remarkably vigorous weather-persistent cloud systems and astonishingly fast winds. This contrast is one of the great puzzles of planetary science. The two planets are similar in size, composition, and age. They formed within the same solar system under broadly comparable conditions. Both receive extremely little sunlight. Yet Neptune somehow maintains a level of atmospheric activity that Uranus does not consistently match. Why? That single question hints that something important is happening beneath Neptune's clouds. Perhaps its interior is releasing heat more efficiently. Perhaps ancient events shaped the two planets differently. Perhaps differences invisible from the outside determine everything we observe above the clouds. Scientists continue investigating all of these possibilities. As telescopes became more powerful throughout the 20th century, Neptune slowly revealed subtle changes. Bright clouds drifted across its atmosphere. Dark regions appeared and vanished. Temperatures varied unexpectedly. Seasonal changes unfolded over years and decades, because one Neptunian year lasts about 165 Earth years. Everything about Neptune moves on timescales unfamiliar to human life. A single season there can last longer than an average human lifetime. Yet within those immense seasons, storms evolve with surprising speed. Winds race around the planet in mere hours. Clouds form and dissipate within days. Vast atmospheric systems emerge and disappear over only a few years. Slow and fast coexist in extraordinary ways. Its orbit belongs to geological time. Its weather belongs to meteorological time. The result is a planet that constantly challenges intuition. By the late 20th century, astronomers had assembled a picture of Neptune that was both coherent and deeply unsettling. The outermost giant planet was not behaving like a frozen relic at the edge of the solar system. Instead, it appeared active, dynamic, and strangely energetic. The familiar model of a quiet cold frontier was beginning to crack. Those first cracks would soon widen dramatically when astronomers measured something that seemed almost impossible. The winds of Neptune were not merely strong. They were among the fastest ever found on any planet. For centuries, wind seemed like one of the most familiar forces in nature. It bends trees, carries clouds, shapes coastlines, and fills the sails of ships. On Earth, even the most powerful hurricanes eventually lose their strength, because the atmosphere can draw only so much energy from the oceans and the sun. The laws of physics place practical limits on how fast weather systems can move. Those same laws apply everywhere. Whether on Earth, Mars, Jupiter, or Neptune, winds arise because air moves from one region to another in response to differences in pressure, temperature, and rotation. The details vary from planet to planet, but the underlying principles remain remarkably consistent. That consistency is precisely why Neptune became such a surprise. When astronomers first began measuring the movement of clouds across its atmosphere, they expected respectable winds. After all, the giant planets are known for energetic weather. Jupiter's colourful bands race around the planet at hundreds of kilometres per hour. Saturn also hosts powerful jet streams that circle its globe with astonishing speed. Neptune surpassed them both. Cloud features drifting through its atmosphere revealed winds reaching nearly 100 kilometers per hour. Some measurements suggested localized speeds even higher. On Earth, these values would exceed the speed of sound under familiar atmospheric conditions, even allowing for the different temperatures and composition of Neptune's atmosphere. These winds occupy an extraordinary place among the fastest planetary air currents ever measured. The obvious question followed immediately: how? The mystery was not simply the number itself. It was where the energy came from. Every moving atmosphere requires a continual supply of energy. Friction slows motion, turbulence dissipates it. Storms gradually consume the very differences in temperature and pressure that created them. Without fresh energy entering the system, even the strongest winds eventually weaken. Earth demonstrates this every day. A hurricane crossing warm tropical water grows because heat continuously rises from the ocean into the atmosphere. Move the same storm over cooler water or dry land, and its energy source disappears. Gradually, the circulation weakens until little remains beyond scattered rain clouds. Neptune possesses no warm tropical oceans. In fact, the sunlight reaching its atmosphere is roughly 900 times weaker than the sunlight falling on Earth. At that distance, solar heating alone seems incapable of driving the immense pressure differences needed to sustain such extreme winds. Something else must be contributing. The discovery forced scientists to reconsider assumptions that had quietly guided planetary science for decades. Perhaps sunlight was never the primary engine. Perhaps the atmosphere was being driven from below. Perhaps Neptune's weather is less like Earth's and more like steam rising from a pot whose heat source remains hidden beneath the surface. The comparison is imperfect, but it captures an important idea. When energy emerges from a planet's interior, it does not simply warm the atmosphere uniformly. Rising heat creates unstable layers. Warmer material moves upward while cooler material sinks. Rotation then stretches these motions into long bands, swirling vortices, and enormous jet streams that can wrap completely around the planet. On Jupiter, this process produces alternating belts and zones that have persisted for centuries. On Neptune, however, the result appears even more extreme. The atmosphere itself is surprisingly thin compared with the immense size of the planet. The visible clouds occupy only the uppermost portion of a vast envelope extending thousands of kilometers downward. Beneath those familiar cloud tops lie increasingly dense layers where hydrogen, helium, methane, water, and ammonia experience pressures unlike anything naturally encountered on Earth. The winds we observe are therefore only the outer expression of processes occurring far below. It is rather like watching waves on the surface of an ocean while knowing that unseen currents deep beneath are steering everything above. Observing those currents directly is impossible. Instead, astronomers must infer their existence through careful measurements. Clouds become tracers, temperatures become clues, spectra reveal the movement of gases. Computer simulations test whether proposed mechanisms can reproduce the observed atmosphere. Each piece of evidence resembles a fragment of a puzzle whose complete picture remains hidden. One particularly intriguing feature is that Neptune's winds do not all move in the same direction. Near the equator, winds generally flow westward opposite the planet's rotation. At higher latitudes, powerful eastward jets emerge instead. These alternating bands resemble the atmospheric circulation seen on Jupiter and Saturn, yet they differ in both strength and structure. The result is an atmosphere of remarkable complexity. Clouds moving at different latitudes can race past one another at enormous relative speeds. Massive storms become trapped within these circulating bands, carried around the planet while simultaneously evolving under changing conditions. Some survive for years. Others disappear almost as mysteriously as they formed. Even more curious is the appearance of brilliant white clouds floating high above Neptune's deeper blue atmosphere. These clouds are not made of water droplets like those on Earth. At the frigid temperatures near Neptune's upper atmosphere, methane condenses into tiny ice crystals. Sunlight reflects brilliantly from these frozen particles, creating luminous streaks and patches that drift through the darker surroundings. They often appear near the edges of giant storms where rising air cools enough for methane ice to form. In this sense, the clouds themselves reveal invisible motions. Where astronomers see bright methane clouds, they infer rising air. Where clouds disappear, sinking air may dominate instead. The atmosphere becomes readable, almost like a map drawn in vapour. Yet every new observation seemed to deepen the paradox. If Neptune's interior supplies sufficient energy to power these extraordinary winds, why does neighbouring Uranus appear so much quieter? Both planets formed from similar materials. Both reside in the frozen outer solar system. Both possess comparable masses and sizes. Yet Neptune seems restless, while Uranus often appears comparatively subdued. The contrast suggests that the answer cannot depend on distance from the Sun alone. Something within Neptune's history or interior must differ in a profound way. Scientists have proposed several possibilities. Perhaps Neptune retained more heat from its formation. Perhaps its internal layers mix more efficiently, allowing energy to escape. Perhaps an ancient collision altered Uranus in ways that trapped its internal heat while leaving Neptune comparatively undisturbed. Each idea has supporting evidence. Each also faces important unanswered questions. For now, no single explanation fully accounts for everything we observe. That uncertainty is not a weakness of science. It is an invitation. Every precise measurement narrows the range of possibilities. Every improved telescope refines the picture. Every computer model eliminates some explanations while strengthening others. Progress often comes not through dramatic revelations, but through countless small improvements accumulating over decades. Neptune reminds us that nature is under no obligation to satisfy our expectations. The farther astronomers looked, the more apparent it became that this distant world was governed by processes far more subtle than anyone had anticipated. And before anyone could even begin to explain those processes, it was worth remembering something remarkable. Humanity did not discover Neptune by accident. Long before anyone saw its blue disk through a telescope, mathematics had already pointed silently toward its existence. The story of that prediction is one of the most extraordinary chapters in the history of astronomy. Long before Neptune became known as a world of supersonic winds and hidden heat, it existed only as a suspicion. No telescope had revealed it. No observer had recorded its pale blue light. Yet somewhere beyond Uranus, something unseen seemed to be exerting a quiet influence on the solar system. It was not visible. It was mathematical. For centuries, astronomers had grown increasingly confident that the motions of the planets could be predicted with extraordinary precision. Since the time of Isaac Newton, gravity had become more than an explanation for falling apples or orbiting moons. It had become a universal language. Given enough observations, the future positions of planets could be calculated years, even decades, in advance. The solar system appeared almost like an immense clock. Each planet followed its own path around the Sun, guided by gravity with astonishing reliability. Small differences could arise from the gravitational pulls of neighbouring planets, but those influences could also be calculated. In principle, nothing should happen without a reason. Then Uranus began to misbehave. After its discovery in 1781 by William Herschel, astronomers carefully tracked its orbit. At first, everything seemed perfectly normal, but as more observations accumulated over the following decades, subtle discrepancies appeared. Uranus was never dramatically out of place. Its orbit differed by only tiny amounts from the predictions. Sometimes it seemed to move slightly ahead of where calculations expected it to be. At other times it lagged slightly behind. The deviations were so small that they might easily have been dismissed as observational errors. Telescopes of the early 19th century were far from perfect. Measuring the precise position of a distant planet against countless background stars demanded extraordinary patience and skill. Yet the discrepancies refused to disappear. The longer astronomers observed Uranus, the clearer it became that something was gently disturbing its motion. Several explanations were possible. Perhaps Newton's law of gravity became inaccurate at enormous distances. Perhaps the observations themselves contained hidden errors. Or perhaps another planet still invisible was tugging on Uranus through gravity. The third possibility was the most daring. How could anyone search for a planet that no one had ever seen? The answer was surprisingly elegant. Rather than searching the sky at random, astronomers decided to let gravity reveal its location. If an unseen planet existed, its mass and approximate position could be inferred from the tiny changes it produced in Uranus's orbit. Instead of asking, "Where is the planet?" they asked a more subtle question. What kind of planet would produce exactly these disturbances? This was an extraordinarily difficult mathematical problem. Gravity works in both directions. Every object influences every other object, and over decades, those influences accumulate into an intricate celestial dance. Reconstructing an unseen participant from only its gravitational fingerprints demanded calculations of remarkable precision. Independently, two young mathematicians accepted the challenge. In England, John Couch Adams began calculating where the unknown planet ought to be. Almost simultaneously in France, Urbain Le Verrier undertook the same task without knowing the full extent of Adams's work. Both men approached the problem from different directions. Both trusted Newton's laws completely, and remarkably both arrived at nearly the same conclusion. Somewhere beyond Uranus, another giant planet was waiting. The calculations themselves were astonishing, but they were not enough. Someone still needed to point a telescope toward the predicted position. That opportunity came in September 1846. At the Berlin Observatory astronomer Johann Gottfried, Galle received Le Verrier's predicted coordinates together with a request that seemed almost unbelievable. Please look here. Using detailed star charts prepared by Heinrich Louis d'Arrest, Galle compared the stars visible through the telescope with those recorded on the chart. One object did not belong. It appeared star-like at first glance, but it occupied a position where no star should have been. Further observations over the following nights confirmed that it was moving. Within roughly 1 degree of Le Verrier's prediction, Neptune had been found. It remains one of the greatest triumphs in the history of science. A planet had effectively been discovered with mathematics before it was discovered with light. The achievement demonstrated something profound. Gravity could reveal invisible worlds. Long before spacecraft digital detectors or powerful space telescopes existed, careful reasoning had extended human perception billions of kilometers beyond direct observation. Today, astronomers routinely use similar ideas to discover planets orbiting distant stars. Tiny gravitational effects reveal worlds too faint to see directly continuing a tradition that Neptune helped establish nearly 2 centuries ago. Yet Neptune's discovery also carried an unexpected lesson. Finding a planet and understanding it are entirely different achievements. For decades after 1846, Neptune remained little more than a tiny bluish point of light. Even the largest telescopes could reveal almost no surface detail. Its enormous distance reduced the entire planet to a small disk with few visible features. Astronomers could estimate its orbit, measure its brightness, and gradually determine its mass through the motions of its moons. But Neptune itself remained largely unknowable. Its atmosphere was hidden. Its storms were invisible. Its rings had not yet been confirmed. Its magnetic field was completely unknown. Even its remarkable weather lay concealed beneath the limits of 19th century technology. As the 20th century progressed, larger telescopes slowly improved the picture. Spectroscopy revealed the presence of methane, explaining Neptune's distinctive blue colour. Careful observations detected subtle variations in brightness, hinting that clouds or storms might exist. Still, the details remained frustratingly elusive. The outermost giant planet was like a distant island glimpsed only through morning mist. Astronomers knew it was there. They knew roughly how large it was. They knew it possessed moons, but its true nature remained hidden behind distance itself. Only one solution existed. If telescopes could not bring Neptune close enough, humanity would have to send a machine across the solar system. Such a mission would require decades of planning, years of travel and engineering on an unprecedented scale. When that spacecraft finally arrived, it would not merely confirm what astronomers already suspected, it would reveal a world that almost no one had expected to find. The journey from Earth to Neptune is not measured simply in kilometers, it is measured in diminishing light. Each time a spacecraft crosses the orbit of another planet, the sun appears a little smaller. Shadows soften, daylight fades. The brilliant star that dominates Earth's sky gradually shrinks into an intensely bright point, surrounded by an ever-expanding darkness. By the time one reaches Neptune, the sun no longer rules the sky in the familiar way. It still shines, of course, but its warmth has become almost symbolic. From Neptune's cloud tops, the sun appears only about 1/400th as wide as it does from Earth. At noon, its light resembles a brilliant star rather than the overwhelming presence we know. Even at midday, the illumination is comparable to a heavily overcast afternoon on Earth. Yet this is the brightest part of a Neptunian day. The planet lives in permanent twilight, and yet despite that faint sunlight, Neptune commands an enormous presence. Its diameter measures nearly 49,250 kilometers, making it almost 4 times wider than Earth. More than 57 Earths could fit inside its volume. Although it is slightly smaller than Uranus in diameter, Neptune contains more mass, making it the densest of the giant planets. Density tells an important story. Jupiter and Saturn are composed predominantly of hydrogen and helium, so much so that their average densities are surprisingly low. Neptune, by contrast, contains a much larger proportion of heavier materials. Rock metal, water, ammonia, and methane all contribute to its structure beneath the outer atmosphere. This is why astronomers classify Neptune as an ice giant rather than a gas giant. The word ice can be misleading. It does not mean Neptune is filled with ordinary frozen ice like the cubes floating in a glass of water. Deep within the planet, pressures become so immense that familiar distinctions between solid, liquid, and gas begin to disappear. Water, for example, behaves in extraordinary ways under these conditions. Laboratory experiments and theoretical models suggest that thousands of kilometers below Neptune's clouds water may exist as a supercritical fluid, a state where liquid and gas merge into something entirely different. Deeper still, under even greater pressure, water molecules may organize into exotic crystalline forms while remaining at temperatures of several thousand degrees Celsius. These are environments unlike any naturally occurring on Earth's surface. The same is true for methane and ammonia. Rather than existing as simple gases, they become compressed into unfamiliar forms governed by immense pressure and temperature. The chemistry of Neptune is therefore not merely colder than Earth's. It is fundamentally different. From the outside, however, the planet appears deceptively simple. Its atmosphere is composed primarily of hydrogen and helium, with a smaller amount of methane. It is that methane which absorbs red wavelengths of sunlight while allowing blue wavelengths to scatter back into space, giving Neptune its rich sapphire appearance. For many years, scientists assumed methane alone explained the planet's deep blue colour. Recent research suggests the story may be more complicated. Comparisons between Uranus and Neptune indicate that additional atmospheric particles or hazes likely influence the precise shade of blue. Both planets contain methane, yet Neptune appears noticeably darker and richer in colour. The exact composition of these hazes remains an active area of research, reminding us that even the colour of a planet can conceal unresolved questions. Beneath those beautiful clouds lies an atmosphere layered like an immense ocean. The uppermost regions are cold enough for methane to freeze into tiny crystals. Deeper layers become warmer and denser until the distinction between atmosphere and interior gradually fades away. Unlike Earth, Neptune has no sharply defined surface. There is no place where a spacecraft could descend and eventually come to rest upon solid ground. Instead, the atmosphere becomes progressively thicker with depth. Pressure rises relentlessly. Clouds give way to denser fluids. Eventually, conditions become so extreme that ordinary materials are transformed into exotic states, governed by pressures millions of times greater than those at Earth's sea level. One could say that Neptune is all atmosphere, or one could say that its atmosphere slowly becomes its interior. Both descriptions capture part of the truth. Rotation adds another layer of complexity. Despite taking approximately 165 Earth years to complete one orbit around the Sun, Neptune spins rapidly on its axis. A single day lasts only about 16 hours. This rapid rotation profoundly shapes the atmosphere. As rising and sinking gases move across the planet, the rotation bends their paths through the Coriolis effect, organizing enormous air currents into powerful jet streams that encircle the globe. The faster a planet rotates, the more strongly this effect influences atmospheric circulation. Neptune rotates quickly enough to create a remarkably dynamic system despite its distant location. Its magnetic field tells an equally unusual story. On Earth, the magnetic field aligns reasonably closely with the planet's rotation axis. Jupiter also possesses a relatively organized magnetic geometry. Neptune does not. Its magnetic field is tilted by roughly 47 degrees relative to its axis of rotation and is significantly offset from the planet's center. As Neptune spins, its magnetic environment wobbles dramatically through space, producing a magnetosphere unlike that of any other major planet. Why this happens remains uncertain. The most widely accepted explanation is that Neptune's magnetic field is generated not within a central metallic core, but within electrically conducting layers of superionic water and other exotic materials located farther outward in the planet's interior. If true, the unusual geometry of the magnetic field becomes a natural consequence of where the dynamo operates, yet this remains an area of ongoing investigation. Again, Neptune offers evidence without complete certainty. Even its rings contribute to the planet's distinctive character. Unlike the bright, icy rings of Saturn, Neptune's rings are faint, dark, and surprisingly dusty. Some contain curious clumps known as arcs, where material appears concentrated rather than evenly distributed around the planet. These structures should gradually spread out under ordinary orbital dynamics, yet they persist, likely stabilized through subtle gravitational interactions with nearby moons. Nothing about Neptune seems entirely straightforward. Every feature that first appears simple gradually reveals hidden complexity. Its atmosphere hides exotic chemistry. Its color conceals unresolved physics. Its magnetic field challenges conventional models. Its rings behave in unexpected ways. Even before considering its remarkable weather, Neptune already stands apart from every other planet in the solar system. And perhaps nowhere is that uniqueness more striking than within its hidden interior. For somewhere beneath thousands of kilometers of cloud, compressed gases, and superheated fluids lies the source of the energy that refuses to let this distant world grow quiet. Finding that hidden engine would become one of the greatest mysteries in planetary science. At first glance, Neptune seems to break one of the simplest rules of planetary science. The farther a planet lies from the Sun, the less energy it should receive. Less energy should mean lower temperatures, weaker atmospheric circulation, and a gradual fading of weather. By the time we reach the edge of the solar system, it feels natural to expect a world approaching equilibrium where little changes except the slow passage of the seasons. Neptune refuses to settle into that quiet state. When astronomers measure the energy leaving the planet, they find something remarkable. Neptune radiates roughly 2.6 times as much energy as it absorbs from the distant Sun. In other words, the planet is not simply reflecting and re-radiating sunlight. It is producing a substantial surplus of heat from within. That single observation transforms the entire planet. Without it, Neptune would probably be a far calmer world. Its clouds would be less active. Its temperature differences would be smaller. Its powerful winds might never develop. Instead, something deep inside the planet continues to release energy billions of years after Neptune formed. The obvious question is also the most difficult. Why, unlike Earth, Neptune cannot rely on radioactive decay in a relatively small rocky interior to explain such enormous energy. Nor does it experience the tidal heating that powers volcanic activity on Jupiter's moon Io. Its heat must come from somewhere else. To understand the possibilities, we must travel back more than 4.5 billion years to the birth of the solar system itself. Planetary formation is an extraordinarily energetic process. A young star is surrounded by a vast disk of gas dust and ice. Tiny grains collide and stick together. Over millions of years they become pebbles, then boulders, then mountain-sized bodies. Gravity gradually takes over, pulling ever larger objects together. Each collision releases energy. Every impact converts motion into heat. As growing planets become more massive, gravity compresses their interiors. Material falling toward the center releases additional energy, warming the entire body. A newly formed planet is therefore not born cold. It begins its life intensely hot. Over billions of years, that heat slowly leaks away into space. Earth still retains some of this ancient warmth. Much of the heat-driving volcanic activity today is leftover energy from planetary formation, supplemented by radioactive decay within the mantle and core. For giant planets, the story becomes even more interesting. Because Jupiter, Saturn, Uranus, and Neptune are vastly larger than Earth, they stored enormous quantities of gravitational energy during their formation. Their immense interiors have been cooling ever since. Cooling, however, does not happen quickly. A giant planet is almost like an enormous thermal reservoir. Its outer atmosphere loses heat into space, but the deeper layers remain insulated beneath thousands of kilometers of dense material. Energy generated billions of years ago can require immense spans of time to escape. Neptune appears to be releasing that ancient energy unusually efficiently, but efficiency raises another puzzle. If retained formation heat explains Neptune's activity, why does nearby Uranus behave so differently? The two planets formed under similar conditions. They contain comparable materials. They are similar in size. Yet Uranus emits very little excess internal heat compared with Neptune. This contrast is one of the most intriguing mysteries in planetary science. Two worlds that seem almost like siblings have followed strikingly different evolutionary paths. Scientists have proposed several explanations. One possibility is that Uranus experienced a catastrophic collision early in its history. Its axis is tilted by about 98 degrees, causing the planet to rotate almost on its side. Such an extreme tilt strongly suggests that a massive impact occurred during the chaotic early solar system. Perhaps that collision did more than alter Uranus's rotation. Some planetary models suggest it may also have disrupted the planet's internal structure, creating stable layers that trap heat deep inside. If warm material cannot circulate freely upward, much of the ancient formation energy remains locked away beneath the atmosphere. Neptune, in contrast, may never have experienced such a disruptive event. Its interior may remain more thoroughly mixed, allowing heat to escape steadily over billions of years. It is an appealing explanation, yet it remains only a hypothesis. Current observations cannot directly reveal the deep interiors of either planet. Instead, scientists compare computer simulations with the properties that telescopes and spacecraft can actually measure. Another possibility focuses not on collisions but on composition. Although Uranus and Neptune appear broadly similar, even modest differences in the proportions of water, ammonia, methane, rock, and hydrogen could significantly influence how efficiently heat moves through the interior. Small differences deep inside may produce enormous differences at the cloud tops. Nature often works this way. Tiny changes in hidden conditions can shape everything visible above. There is also the possibility that entirely new physics of planetary interiors remains to be discovered. The pressures within Neptune reach several million times Earth's atmospheric pressure. Temperatures climb to thousands of degrees. Molecules behave in unfamiliar ways. Materials that are electrical insulators under ordinary conditions become excellent conductors. Some laboratory experiments suggest that water may enter a remarkable state known as superionic ice. Despite its name, this is neither ordinary ice nor ordinary liquid. The oxygen atoms arrange themselves into a crystalline framework while hydrogen ions move freely through the structure almost like a liquid. The result is a phase of matter that conducts electricity efficiently while remaining solid in one sense and fluid in another. If extensive layers of superionic water exist inside Neptune, they could influence both the transport of heat and the generation of the planet's unusual magnetic field. This remains one of the most exciting frontiers in planetary science. Remarkably, researchers can now reproduce some of these extraordinary conditions using powerful lasers and diamond anvil cells in laboratories on Earth. For brief moments, they create pressures approaching those deep inside ice giants, allowing theoretical predictions to be tested experimentally. Every experiment provides another small clue, yet Neptune continues to guard its deepest secrets. The challenge is that all of these explanations concern regions completely hidden from direct observation. Voyager 2 never saw Neptune's interior. No spacecraft has descended into its atmosphere. No probe has measured conditions thousands of kilometers below the clouds. Everything beneath the visible atmosphere must be reconstructed indirectly, rather like studying the inside of a mountain by listening to echoes from its slopes. Astronomers therefore rely on a remarkable combination of evidence. They measure the planet's gravity. They observe its magnetic field. They track atmospheric motion. They analyze infrared radiation escaping into space. They compare all these observations with increasingly sophisticated computer models. The result is not certainty, it is convergence. Independent lines of evidence gradually point toward explanations that are more likely than others, even if none has yet solved every mystery. This is one of the quiet strengths of science. Answers rarely appear all at once. They emerge as many different pieces begin to agree. Neptune's hidden furnace remains unseen, but its influence is everywhere. It shapes the clouds. It powers the winds. It may determine the magnetic field. It could even explain why this distant blue world differs so profoundly from its closest planetary neighbour. The next step, however, is to understand how scientists can study a planet whose most important processes remain buried beneath thousands of kilometres of atmosphere. To read Neptune, astronomers have learned to treat light itself as a messenger. Neptune has never allowed itself to be studied in the straightforward way. On Earth, a scientist can collect rocks, drill beneath the ground, launch weather balloons, or sail across oceans to measure currents directly. Even on Mars, robotic explorers analyze soil, examine ancient riverbeds, and monitor the atmosphere from the surface. Neptune offers none of these possibilities. It is too distant for routine exploration, too deep for a lander to reach a solid surface, and too hostile for any existing spacecraft to descend very farther into its atmosphere. Every fact we know about this world has been gathered from a remarkable distance, often by studying nothing more tangible than tiny variations in light. In astronomy, light is never merely illumination. It is information. Every photon leaving Neptune carries a small record of where it has been. Some have reflected from methane clouds. Others have passed through layers of gas before escaping into space. Still others originate as invisible infrared radiation emitted by the planet itself. Each photon tells part of a story. The challenge is learning how to read it. One of the most powerful tools available to astronomers is spectroscopy. Although the name sounds technical, the underlying idea is surprisingly simple. When sunlight passes through a prism, it separates into the familiar colours of the rainbow. Yet that rainbow is not perfectly continuous. Certain wavelengths are missing because atoms and molecules absorb very specific colours of light. Each chemical substance leaves behind its own distinctive pattern, rather like a fingerprint. Hydrogen produces one pattern, helium another, methane another still. By spreading Neptune's light into its component wavelengths, astronomers can identify which gases are present in the atmosphere without ever touching the planet itself. This method revealed one of Neptune's defining characteristics. Methane absorbs red light far more efficiently than blue light. As sunlight enters the atmosphere, much of the red portion is removed while shorter blue wavelengths are scattered back towards space. The result is Neptune's familiar deep blue appearance. But spectroscopy reveals far more than colour. It also measures motion. Here the story becomes even more elegant. When an object moves toward an observer, the wavelengths of its light become slightly compressed. When it moves away, the wavelengths become slightly stretched. This subtle effect, known as the Doppler shift, allows astronomers to determine how fast gases are moving even across billions of kilometres. The shifts are extraordinarily small. Yet modern instruments can detect changes corresponding to only a few meters per second. By measuring these tiny displacements across Neptune's atmosphere, researchers gradually assemble a map of winds flowing around the planet. Clouds provide another set of clues. Unlike Earth's water clouds, Neptune's visible clouds consist largely of methane ice crystals forming high in the atmosphere. They drift with surrounding air currents, acting almost like naturally placed tracking markers. Astronomers photograph the planet repeatedly over hours and days. As individual cloud features move, their changing positions reveal the speed and direction of atmospheric circulation. This technique has become increasingly powerful with advances in telescope technology. When Voyager 2 flew past Neptune in 1989, it delivered images of unprecedented clarity. For the first time, scientists could watch enormous cloud systems moving across the planet almost in real time. One storm in particular immediately captured attention. It appeared as a vast dark oval roughly comparable in size to Earth. Voyager scientists named it the Great Dark Spot. Its appearance naturally reminded observers of Jupiter's famous Great Red Spot, which has persisted for centuries. At first, astronomers assumed Neptune's storm might represent another long-lived atmospheric vortex. Then something unexpected happened. A few years later, when the Hubble Space Telescope observed Neptune the Great, dark spot had vanished. It had not simply drifted elsewhere. It appeared to have dissipated completely. Soon afterward, new dark storms formed in different regions of the atmosphere. Some survived for several years. Others disappeared surprisingly quickly. Unlike Jupiter's enduring giant storm, Neptune's large vortices seemed transient, forming and fading over timescales measured in years rather than centuries. Why? Again, observations produce questions faster than answers. Scientists now believe these dark spots are giant atmospheric vortices associated with regions of high pressure. Around their edges, methane-rich air rises and cools, producing brilliant white companion clouds that Voyager also observed. The bright clouds are therefore not separate weather systems. They are visible signatures of the invisible circulation surrounding the storm. Even after Voyager's brief encounter ended, Earth-based telescopes continued the investigation. The introduction of adaptive optics transformed what was possible. Normally, turbulence within Earth's atmosphere blurs astronomical images. Stars appear to twinkle because their light passes through constantly shifting pockets of air. Adaptive optics compensates for this distortion. Powerful computers analyze the changing wavefronts of incoming light hundreds or even thousands of times each second. Flexible mirrors then adjust their shapes almost instantaneously to cancel much of the atmospheric blurring. The result is extraordinary. Large ground-based telescopes can now approach the sharpness once achievable only from space. Observatories such as the W.M. Keck Observatory and the Very Large Telescope routinely monitor Neptune's cloud systems, following storms as they evolve over months and years. Infrared observations add yet another layer of understanding. Visible light reveals reflected sunlight. Infrared radiation reveals heat. Because every object above absolute zero emits infrared energy, astronomers can measure temperatures throughout Neptune's atmosphere by observing different infrared wavelengths. Some wavelengths emerge from high cold layers. Others escape from deeper, warmer regions. Combining these measurements allows scientists to reconstruct a three-dimensional picture of atmospheric structure. Unexpected temperature differences often reveal regions where gases are rising or sinking, helping researchers understand circulation patterns that remain invisible in ordinary photographs. More recently, observations from the James Webb Space Telescope have provided still richer views of Neptune using infrared instruments of unprecedented sensitivity. Features that appear faint or invisible in visible light become strikingly clear in the infrared, allowing astronomers to investigate cloud layers, atmospheric composition, and seasonal changes with remarkable detail. Yet even these magnificent observatories share one important limitation. They observe only the exterior. The hidden engine driving Neptune's atmosphere remains buried beneath thousands of kilometers of dense material. Scientists therefore combine observations with another indispensable tool: computation. Modern supercomputers simulate Neptune's atmosphere by solving millions of equations describing fluid motion, radiation chemistry, and planetary rotation. Researchers adjust internal heat, atmospheric composition, cloud formation, and circulation until the simulations resemble the real planet. Sometimes they succeed remarkably well. Sometimes they fail completely. Those failures are often the most valuable results. Every unsuccessful model eliminates another possible explanation. Every improvement narrows the range of hidden conditions that could produce the Neptune we actually observe. Little by little, the invisible becomes constrained by the visible. The atmosphere becomes a message written in clouds. The light becomes a language. And from that language, astronomers are beginning to reconstruct processes taking place far below the cloud tops, where no telescope can ever directly see. Yet the evidence still permits more than one explanation. To understand Neptune fully, scientists must carefully distinguish between what has been measured, what is strongly supported, what remains hypothetical, and what is still entirely unknown. That distinction becomes the heart of the next stage of our journey. One of the quiet strengths of astronomy is its willingness to live with uncertainty. From the outside, science often appears to provide firm answers. A planet has a certain mass. A star shines with a measurable brightness. A galaxy lies a specific distance away. These facts can create the impression that the universe has gradually surrendered all of its important secrets. The reality is more subtle. The farther we venture from direct observation, the more often certainty gives way to probability. Neptune is an excellent example. Astronomers know its diameter with remarkable precision. They know how long it takes to rotate. They know the composition of its upper atmosphere, the paths followed by its moons, and the strength of its gravitational pull. Yet the most important processes occurring deep inside the planet remain hidden. To understand them, scientists must carefully separate four very different categories of knowledge. First come the observed facts. These are measurements that can be made directly. Neptune radiates substantially more energy than it receives from the Sun. Its atmosphere contains hydrogen, helium, and methane. Its winds reach extraordinary speeds. Its magnetic field is both tilted and offset from the planet's center. Its largest moon, Triton, orbits in the opposite direction from Neptune's rotation. These observations are not matters of opinion. They have been measured repeatedly using different instruments and methods. Next comes the evidence. Evidence differs slightly from observation. An observation tells us what exists. Evidence helps us infer why it exists. For example, the movement of methane clouds provides evidence for powerful atmospheric circulation. Variations in infrared radiation indicate differences in atmospheric temperature. The unusual geometry of Neptune's magnetic field suggests that the internal dynamo operates in an unexpected region, rather than deep within a compact metallic core. Evidence points toward explanations. It does not prove them by itself. Beyond evidence lie hypotheses. These are carefully constructed ideas designed to explain all available observations while remaining consistent with established physics. Several competing hypotheses attempt to explain Neptune's hidden heat. One proposes that Neptune simply retained more of its primordial formation energy than Uranus. Another suggests that Neptune's interior mixes more efficiently, allowing ancient heat to escape steadily into space. A third proposes that Uranus rather than Neptune is the unusual case. Perhaps an enormous collision early in Uranus's history created stable internal layers that trapped its heat, making Neptune appear exceptionally active by comparison. Each hypothesis explains some observations well. None explains everything. That is perfectly normal. Scientific progress rarely begins with a single perfect explanation. Instead, several ideas compete while new evidence gradually favors one over the others. Finally comes the largest category of all, the unknown. There are questions for which no accepted explanation yet exists. Exactly how heat is transported through Neptune's deep interior remains uncertain. The precise composition of some atmospheric hazes is still being investigated. The detailed structure of the magnetic dynamo is not fully understood. Even the mechanisms governing the birth and disappearance of giant dark storms continue to be refined. Acknowledging these unknowns is not a weakness. It is one of science's defining strengths. A theory that honestly identifies its uncertainties is far more reliable than one claiming certainty without evidence. Consider Neptune's magnetic field. On Earth, the explanation is comparatively straightforward. Our magnetic field is generated by convection within a rotating outer core of liquid iron. The moving electrically conducting metal acts as a natural dynamo, continuously producing magnetic fields. Neptune almost certainly operates differently. The planet contains too little metallic iron in the appropriate location to generate its observed field in the same manner. Instead, scientists believe electrically conducting layers rich in water, ammonia, and methane under enormous pressure may act as the dynamo. This hypothesis reproduces many observed features, including the field's unusual tilt. Yet no one has ever measured such an interior directly. The explanation remains the best current model supported by multiple independent observations, but it is still open to refinement. Another fascinating example concerns the possibility of diamond formation. Deep inside, Neptune pressures become so immense that methane molecules may break apart. Carbon atoms released during this process could potentially crystallize into diamonds. Laboratory experiments have shown that carbon-rich materials exposed to conditions similar to those inside ice giants can indeed produce microscopic diamonds. This evidence has given rise to the idea of diamond rain. The phrase captures the imagination immediately, yet it is important to distinguish what is supported from what remains uncertain. The physics suggests that diamond formation is plausible. Experiments support the possibility. Computer models indicate that carbon may separate under extreme pressure, but no spacecraft has observed diamonds falling through Neptune's interior. No instrument has directly measured such a process. Diamond rain therefore remains a scientifically grounded hypothesis rather than an observed fact. It illustrates an important principle. The most interesting ideas in planetary science often occupy the space between certainty and speculation. Researchers neither dismiss them nor accept them uncritically. Instead, they continue searching for evidence. The same careful approach applies to Neptune's internal layering. Some models suggest vigorous convection extending through much of the interior. Others indicate partially stable layers that slow the upward transport of heat. Still others predict transitions between different phases of water and other volatile materials that influence circulation in ways not yet fully understood. Each model reproduces certain measurements. Each fails to reproduce others. Rather than choosing a favorite prematurely, planetary scientists compare every prediction against newly collected data. This continual testing gradually eliminates weaker explanations. It is a slow process, sometimes frustratingly slow. Yet history suggests that patience often proves worthwhile. The discovery of Neptune itself required decades of increasingly precise observations before its existence became undeniable. The understanding of its atmosphere has similarly unfolded over generations. Each new telescope has sharpened the picture. Each spacecraft has expanded the evidence. Each computer simulation has refined the questions. And through it all, one lesson becomes increasingly clear. Nature is often more inventive than our first explanations. The true answer frequently contains elements no one originally anticipated. That possibility makes Neptune especially compelling. Somewhere beneath its cloud tops may lie physical processes unlike those operating anywhere else in the solar system. Processes that influence not only one distant planet, but perhaps countless ice giants orbiting stars throughout the galaxy. If one of the leading ideas about Neptune's interior is correct, its consequences extend far beyond atmospheric winds or magnetic fields. They reach into the very structure of the planet itself. To explore those consequences, we must ask a simple but profound question. What if Neptune's hidden interior has never truly stopped moving since the day the planet was born? A planet is often described as though it were a finished object. We speak of Earth's mountains, Mars's volcanoes, or Neptune's atmosphere, as though each world reached its final form billions of years ago, and has remained essentially unchanged ever since. The language is convenient, but it can also be misleading. Planets are not monuments. They are ongoing processes. Even after billions of years, they continue to cool, circulate, compress, and evolve. Some do so quietly. Others reveal their internal activity through volcanoes, earthquakes, magnetic fields, or changing atmospheres. Neptune belongs firmly in that second group. Although no one has ever seen beneath its cloud tops, nearly every observation suggests that the planet's interior remains remarkably active. The visible atmosphere may simply be the outermost expression of motions occurring thousands of kilometers below. Suppose for a moment that this picture is essentially correct, not as a proven fact, but as a scientifically grounded thought experiment. Suppose Neptune's deep interior has never truly become still. What would follow? The first consequence would be continuous convection. Convection is one of nature's simplest yet most powerful mechanisms for transporting energy. Warm material becomes less dense and rises. Cooler material becomes denser and sinks. This circulation carries heat from the interior toward the surface without requiring the entire object to warm uniformly. On Earth, convection occurs inside the mantle in the oceans and throughout the atmosphere. The slow motion of Earth's mantle drives plate tectonics over millions of years. The rapid convection of warm air creates thunderstorms within hours. The same physical principle operates across vastly different scales. Inside Neptune, however, the materials involved are unlike anything familiar. Instead of circulating molten rock or liquid water, convection likely involves dense mixtures of hydrogen, helium water, ammonia, methane, and exotic high-pressure fluids. These enormous convective cells may span thousands of kilometers. Their motions are slow compared with atmospheric winds, yet over decades, centuries, and millions of years they transport astonishing amounts of energy upward. As this energy approaches the upper atmosphere, something remarkable begins to happen. The deep circulation does not simply warm the clouds. It creates differences. Some regions receive more heat than others. Some gases rise while neighboring regions sink. Temperatures vary slightly from place to place. Pressure responds accordingly. Those seemingly modest differences become the seeds from which Neptune's immense weather systems grow. A giant storm does not suddenly appear from nowhere. It develops because countless small motions gradually organize into larger structures. This is true on Earth. It may be even more true on Neptune. Rapid planetary rotation then amplifies these developing patterns. As rising currents move toward higher altitudes, Neptune's 16-hour day bends their paths through the Coriolis effect. Instead of spreading randomly across the globe, atmospheric motion becomes organized into long jet streams circling the planet. These jets separate regions moving at different speeds and even in different directions. When neighboring air masses interact, instability develops. Instability gives birth to vortices. Vortices grow into storms. Storms reshape the atmosphere. The entire system becomes a continuous cycle rather than a collection of isolated events. One observation strongly supports this picture. Neptune's brightest methane clouds often appear above regions where models predict vigorous upward motion. As warmer gases rise from below, they expand into lower pressure environments and cool. Eventually, methane reaches temperatures low enough to condense into tiny ice crystals. Those crystals scatter sunlight, efficiently producing the brilliant white clouds observed by Voyager 2 and later by Earth-based telescopes. In this sense, the clouds are not merely weather. They are visible markers of energy escaping from deep inside the planet. Every bright cloud hints at hidden convection far below. If this interpretation is correct, Neptune's atmosphere resembles the glowing surface of a fireplace. The visible flames tell us almost nothing about the detailed arrangement of burning wood beneath them, yet they unmistakably reveal that combustion continues. The atmosphere performs a similar role. It reveals activity without exposing its ultimate source. The consequences extend beyond weather. A continuously convecting interior could also explain Neptune's unusual magnetic field. Magnetic dynamos require two essential ingredients. First, electrically conducting material. Second, sustained motion. Without motion, magnetic fields gradually decay. With continual circulation, fresh magnetic fields are constantly generated. If Neptune's deep layers remain in vigorous motion, they naturally provide the conditions needed for an active dynamo. The unusual geometry of the field may simply reflect the shape and location of those circulating conductive layers. Again, this remains a leading interpretation rather than established fact. Yet it unites several otherwise puzzling observations within a single framework. The atmosphere, the magnetic field, the internal heat, all become different expressions of one underlying process. Planetary evolution, there may be another consequence as well. Convection mixes material. Without mixing, heavier substances gradually sink while lighter materials remain above. Strong circulation continually redistributes chemical components throughout the interior. This influences not only the transport of heat, but also the long-term chemical evolution of the planet itself. The atmosphere we observe today may therefore differ substantially from the atmosphere Neptune possessed billions of years ago. Tiny changes accumulate over immense spans of time. A planet slowly rewrites its own history. Computer simulations increasingly suggest that such long-term evolution is inevitable. The precise details differ from one model to another, but many indicate that Neptune's interior has likely changed continuously since the solar system formed. Layers shift, boundaries migrate, heat escapes, chemical compositions evolve. The planet is not static, it is aging. Remarkably, this gradual evolution may also explain why Neptune still surprises astronomers today. A planet changing over billions of years need not settle into perfect equilibrium. Instead, it may experience phases of greater or lesser activity depending on how efficiently internal heat reaches the atmosphere. The Neptune we observe now represents only one moment within an immensely long history. Had intelligent observers existed a billion years ago, they might have seen a somewhat different planet. A billion years from now, future observers may see another. This realization subtly changes our perspective. We often think of planets as places. Astronomy increasingly encourages us to think of them as stories. Each world has a beginning. Each evolves through time. Each preserves traces of ancient events while continuously creating new ones. Neptune's storms are chapters within that story rather than permanent features. Its hidden heat is not simply property. It is part of an unfolding process extending across the age of the solar system. If this view is broadly correct, then Neptune becomes far more than an isolated curiosity. It becomes a natural laboratory for understanding one of the most common categories of planets in our galaxy. Thousands of exoplanets discovered around distant stars resemble Neptune more closely than they resemble Earth. Some orbit close to their stars. Others occupy colder, more distant regions. Many likely possess deep atmospheres, exotic interiors, and internal heat sources of their own. By understanding one nearby ice giant, astronomers gain insight into countless distant worlds they may never observe in comparable detail. Neptune ceases to be merely the solar system's outer blue planet. It becomes a representative of an entire family of planets scattered throughout the Milky Way. The mystery therefore grows rather than shrinks. To understand Neptune is to begin understanding worlds orbiting stars hundreds or thousands of light years away. Our next step is to widen the view even further, for Neptune's hidden engine does not belong only to one planet. It belongs to a much larger story about how planets throughout the universe are born, evolve, and continue changing long after their stars first ignite. For much of human history, the solar system was our only example of how planets could exist. There was Earth with its oceans and continents. There were the rocky inner worlds, the giant outer planets, and the distant belt of icy bodies beyond Neptune. From this single planetary family, we naturally formed our expectations about how planetary systems should be built. Then the universe quietly became much larger. In the early 1990s, the first confirmed planets orbiting ordinary stars beyond the Sun were discovered. At first, they seemed almost unbelievable. Some were giant worlds orbiting astonishingly close to their stars, completing an orbit in only a few days. Others occupied paths unlike anything seen in our own solar system. As the discoveries accumulated, one lesson became impossible to ignore. Our solar system is only one arrangement among many. Today, astronomers have confirmed thousands of exoplanets with many thousands more awaiting confirmation. These worlds display an astonishing variety of sizes, temperatures, compositions, and orbital architectures. Some are smaller than Earth. Others are larger than Jupiter. Some circle pairs of stars. Others travel on elongated orbits that would seem chaotic if found within our own planetary neighbourhood. Yet among all these discoveries, one category appears again and again. Planets remarkably similar in size to Neptune. This came as a surprise. If one were to examine only the solar system, it would be easy to assume that rocky planets like Earth or giant planets like Jupiter represent the most common outcomes of planetary formation. The exoplanet surveys told a different story. Worlds between Earth and Neptune in size, along with Neptune-like planets themselves, appear to be among the most abundant types of planets in the Milky Way. Curiously, our own solar system contains no planet that falls neatly into the most common size category found elsewhere. Earth is smaller. Neptune is larger. Between them lies an apparent gap. This realization transformed Neptune from an interesting outer planet into something much more significant. It became one of the closest laboratories for studying a class of planets that may populate the entire galaxy. Of course, not every Neptune-like planet is identical. Some orbit so close to their stars that their atmospheres reach temperatures of more than 1,000 degrees Celsius. These so-called hot Neptunes experience conditions completely unlike those found in our own solar system. Others orbit at intermediate distances where temperatures are milder. Still others may exist in distant cold regions much like Neptune itself. Despite these differences, many likely share fundamental characteristics. Deep hydrogen-rich atmospheres, interiors containing large quantities of water and other volatile materials, long-term internal heat, powerful atmospheric circulation. By understanding the physical principles operating within Neptune, astronomers develop tools that can be applied across an enormous range of planetary environments. This connection is possible because physics is remarkably consistent. Gravity behaves the same everywhere. Fluid dynamics obeys the same equations whether describing Earth's atmosphere or the clouds of an exoplanet hundreds of light years away. Atoms absorb and emit light according to the same quantum rules throughout the universe. The details differ. The underlying laws do not. This allows astronomers to use Neptune as something more than a destination. It becomes a reference point. When a distant exoplanet passes in front of its parent star, a tiny fraction of starlight filters through the planet's atmosphere before reaching our telescopes. Different gases absorb different wavelengths. Just as spectroscopy reveals methane in Neptune's atmosphere, it also reveals water vapor, carbon dioxide, sodium, methane, and other substances within distant planetary atmospheres. Often, however, the data are incomplete. A telescope may detect only a handful of spectral features. Interpreting those observations requires atmospheric models. Those models are tested, refined, and calibrated using planets much closer to home. Neptune therefore helps scientists interpret worlds they cannot visit. Its atmosphere provides an anchor for understanding many others. The relationship works in both directions. Exoplanets also challenge our understanding of Neptune. Some Neptune-sized worlds appear much puffier than expected, suggesting atmospheres inflated by intense stellar heating. Others seem unusually dense, implying different internal compositions. Some appear to be slowly losing their atmospheres under the powerful radiation of nearby stars. Each new discovery broadens the range of possible planetary evolution. The more worlds astronomers find, the more they realize that Neptune represents only one expression of a much larger family. Yet it remains uniquely valuable because it is close enough to study in detail. There is another important connection. Planetary formation, Modern theories suggest that giant planets form within disks of gas and dust surrounding young stars. As growing planetary cores accumulate enough mass, they begin attracting enormous quantities of hydrogen and helium from the surrounding disk. Exactly how this process unfolds remains an active area of research. Why do some worlds become Jupiter-sized giants while others stop growing near Neptune's mass? Why do some migrate inward toward their stars while others remain in distant orbits? How much does the timing of formation matter? How important are collisions between young planets? Neptune cannot answer these questions by itself, but it provides essential evidence. Its composition preserves clues about the materials available in the outer solar system during its formation. Its orbit reflects the gravitational history of the young solar system. Its moons record ancient dynamical interactions. Its interior carries information about billions of years of planetary evolution. Each piece contributes to a broader picture extending far beyond our own Sun. The remarkable thing is that none of this was obvious when Neptune was first discovered. To 19th century astronomers, it was simply another distant planet. To modern planetary science, it has become a key to understanding an entire population of worlds throughout the galaxy. The farther our telescopes reach into space, the more relevant Neptune becomes. Yet perhaps the most surprising lesson has nothing to do with exoplanets. It comes from much closer to Neptune itself. For orbiting this restless blue giant is an object that seems almost out of place. Unlike the regular moons circling Jupiter or Saturn, Neptune's largest satellite tells a story of capture rather than birth. Its orbit runs backward, its surface is unexpectedly young, its interior may still be active, and its very existence may have transformed the entire Neptunian system. To understand Neptune completely, we must now turn our attention away from the planet itself and toward the extraordinary companion that has been quietly shaping its history for billions of years. The giant planets of the solar system each possess families of moons. At first glance, these families appear to follow a familiar pattern. Most large moons orbit in the same direction that their planets rotate. Their paths are nearly circular, and they travel close to the planet's equatorial plane. These characteristics suggest that they formed alongside their parent planets, condensing from the same disks of gas and dust that surrounded the young giants billions of years ago. Jupiter's 4 largest moons fit this picture beautifully. Many of Saturn's major moons do as well. Even Uranus, despite its unusual axial tilt, retains a system of regular satellites that generally follows the expected pattern. Neptune, however, tells a different story. Its largest moon does something remarkable. It moves backward. Astronomers describe such an orbit as retrograde. Instead of travelling around Neptune in the same direction that the planet rotates Triton circles in the opposite direction. This single observation carries profound implications. A large moon cannot easily form in a retrograde orbit around a giant planet. If Neptune and Triton had condensed together from the same rotating disk of material, both would naturally have inherited the same direction of motion. The simplest explanation is therefore not formation. It is capture. At some point in the distant past, Triton almost certainly formed elsewhere before becoming trapped by Neptune's gravity. That conclusion immediately raises another question. How does a planet capture a moon nearly as large as Triton? Gravity alone cannot usually accomplish this. An object approaching a planet typically accelerates during the encounter and then escapes again along a different trajectory. To remain permanently bound, it must lose enough energy during the encounter. That is surprisingly difficult. Several capture mechanisms have been proposed. Among the leading ideas is that Triton originally belonged to a binary system, a pair of icy bodies orbiting one another much like the dwarf planet Pluto and its large moon Charon. If such a binary passed sufficiently close to Neptune, the planet's enormous gravity could have disrupted the pair. One object would escape. The other would lose enough orbital energy to remain permanently bound to Neptune. Computer simulations show that this process is physically plausible. Although rare, such encounters become possible over the immense timescales available during the early solar system. If this interpretation is correct, Triton did not begin its existence as Neptune's moon. It was captured from the distant population of icy bodies that still occupies the outer reaches of the solar system. Today, many astronomers regard Triton as a close relative of Pluto and other large objects inhabiting the Kuiper Belt. Its appearance supports this idea. Triton's surface is composed largely of water, ice, nitrogen ice, carbon dioxide ice, and methane ice. At first glance, such a frozen landscape might seem geologically dead. Voyager 2 revealed something quite different. When the spacecraft flew past Triton in 1989, it photographed one of the most unexpected sights in planetary exploration. Dark plumes rising above the icy surface. These were interpreted as active geysers ejecting nitrogen gas and dark particles several kilometers into the thin atmosphere, before the material drifted back to the ground. At the time, Triton became only the second body beyond Earth where active geological processes had been directly observed. The discovery suggested that even in the extreme cold of the outer solar system, planetary activity can persist. The source of that activity remains an active area of study. Some energy may come from seasonal heating by the distant sun. Additional heat may arise from radioactive decay within Triton's rocky interior. Most importantly, tidal forces generated during Triton's gradual orbital evolution may have warmed the Moon significantly in the past. That history matters. When Triton was first captured, its orbit was probably highly elongated. Each close approach to Neptune would have produced powerful tidal flexing, repeatedly stretching and compressing the Moon's interior. The process resembles what occurs today on Jupiter's moon Io, although under different circumstances. Mechanical deformation generates heat. Heat drives geological change. Over millions of years, tidal energy would gradually have circularized Triton's orbit, while profoundly altering both the Moon and the Neptunian system. The consequences for Neptune itself may have been enormous. Before Triton's arrival, Neptune almost certainly possessed a regular family of moons orbiting in orderly prograde paths. The capture of such a massive object would have disrupted that delicate arrangement. Computer simulations suggest many original moons may have collided with one another, fallen into Neptune, or been ejected from the system entirely. Triton did not merely become another moon, it likely reshaped the entire architecture of Neptune's satellites. Even Neptune's faint rings may preserve echoes of that ancient upheaval. Dust generated by collisions between shattered moons could have contributed material to the ring system observed today. Although billions of years have passed, the planet may still carry subtle traces of that distant gravitational encounter. The story grows even more intriguing when we look toward the future. Unlike Earth's moon, which slowly moves away from our planet, Triton is gradually spiraling inward. Its retrograde orbit causes tidal interactions that steadily remove orbital energy. The process is extraordinarily slow. It'll require billions of years. Yet if nothing interrupts this evolution, Triton will eventually approach Neptune closely enough to cross a critical boundary, known as the Roche limit. Beyond that point, Neptune's tidal forces would overwhelm Triton's own gravity. The Moon would be torn apart. Its icy fragments could spread into an immense ring system, potentially rivaling or even exceeding Saturn's in grandeur. For a time, Neptune might become the most spectacular ring planet in the solar system. That future remains distant beyond ordinary human comprehension. Nevertheless, it reminds us that planetary systems continue evolving long after their formation. Nothing remains permanently fixed. Moons migrate. Rings appear and disappear. Impacts reshape histories. Even giant planets experience continual change. Triton therefore serves as more than an unusual satellite. It provides a bridge connecting several of the themes we've encountered throughout our journey. Hidden internal energy, long-term planetary evolution, gravitational interactions, the persistence of geological activity in unexpected places. Most importantly, Triton demonstrates that Neptune's present appearance cannot be understood simply by examining the planet itself. Its history is written across an entire planetary system. Every moon, every ring, every orbit preserves fragments of a story stretching back to the earliest days of the solar system. Modern astronomy is now uncovering those fragments with instruments far more capable than anything available during Voyager's brief visit. The picture continues to sharpen. Yet with every improvement, Neptune seems determined to reveal another layer of complexity. When Voyager 2 departed Neptune in August 1989, it left behind more than a distant blue planet. It left behind an unfinished conversation. For a few remarkable hours, humanity had observed Neptune with a clarity that no telescope on Earth could match. The spacecraft photographed storms, measured magnetic fields, analysed the atmosphere, discovered new rings, and revealed the astonishing complexity of Triton. Then it continued outward. No spacecraft has returned since. At first, this seems almost surprising. More than 3 decades have passed. During that time, spacecraft have repeatedly explored Mars-orbited Saturn, for 13 years landed on a comet, visited Pluto, and flown through the asteroid belt. Neptune, meanwhile, has remained alone. Yet planetary science has not stood still. While no probe has revisited the distant ice giant, the tools available to astronomers have changed almost beyond recognition. Telescopes have grown larger. Detectors have become vastly more sensitive. Computer simulations now solve problems that would have been impossible only a generation ago. Without leaving Earth, scientists have continued watching Neptune evolve. One of the greatest advances has come from observing the planet over long periods of time. Voyager saw Neptune during only a brief moment in its long seasonal cycle. That snapshot was invaluable. But a snapshot cannot reveal climate. Neptune requires patience. 1 year on Neptune lasts about 165 Earth years. Each season therefore extends for more than 4 decades. A child born during Voyager's flyby would still not have witnessed the end of a single Neptunian season. This immense timescale changes the way astronomers think. Instead of asking what Neptune looks like today, they ask how it changes over decades. Repeated observations have revealed that its atmosphere is anything but static. Bright methane clouds appear, drift, and disappear. Dark vortices emerge unexpectedly before fading away. Temperatures vary subtly across latitudes. Even the overall brightness of the planet changes over time. These variations suggest that Neptune possesses something resembling climate in addition to weather. Weather describes short-term events. Climate describes long-term patterns. On Neptune, the distinction unfolds over decades rather than years. The ability to monitor these slow changes has improved dramatically through the combined efforts of multiple observatories. The Hubble Space Telescope has repeatedly imaged Neptune since the 1990s, producing an extraordinary visual record of atmospheric evolution. 1 year, a giant dark storm dominates a hemisphere. Several years later, it has vanished. Elsewhere, a new vortex begins to form. Rather than being permanent structures, Neptune storms appear to have life cycles. They are born, they evolve, they dissipate. Then the atmosphere begins the process again. Ground-based observatories have contributed equally important observations. The W.M. Keck Observatory and the Very Large Telescope use adaptive optics to achieve astonishing clarity despite Earth's turbulent atmosphere. By comparing images collected over many nights, astronomers track cloud motions with remarkable precision. These observations continually refine measurements of wind speeds and atmospheric circulation. Perhaps the most exciting recent advance has come from the James Webb Space Telescope. Unlike Voyager, which raced past Neptune during a single encounter, Webb can return again and again, observing the planet across infrared wavelengths unavailable to human vision. Infrared light reveals information invisible in ordinary photographs. Different wavelengths emerge from different depths within the atmosphere. Some originate near the highest methane clouds. Others escape from warmer layers below. By combining these observations, astronomers build increasingly detailed vertical profiles of Neptune's atmosphere. Webb has also provided striking views of Neptune's rings. Although faint in visible light, the rings appear with remarkable clarity in certain infrared wavelengths, revealing delicate structures that are difficult to observe from Earth. Even Triton takes on a different appearance in the infrared, reflecting sunlight with extraordinary brightness because of its icy surface. These observations remind us that every wavelength tells a different story. Visible light shows one Neptune, infrared reveals another. Radio observations reveal yet another. No single instrument provides the complete picture. Modern astronomy succeeds by combining them all. Meanwhile, advances in computation have become just as important as advances in observation. The most sophisticated planetary simulations now model fluid dynamics in 3 dimensions while simultaneously accounting for radiation chemistry, cloud formation, planetary rotation, and internal heat transport. Such calculations require enormous computational power, yet they allow scientists to perform experiments impossible in reality. researchers can slightly increase Neptune's internal heat, change the atmospheric composition, modify cloud physics, alter rotation rates, then compare the simulated atmosphere with actual observations. When a model reproduces Neptune's measured winds, temperatures, and cloud patterns, confidence in its underlying assumptions increases. When it fails, scientists learn just as much. Each unsuccessful simulation eliminates another possible explanation. Machine learning has also begun assisting this process. Rather than replacing physical understanding, machine learning helps identify subtle patterns hidden within enormous observational datasets. Cloud motions too complex for manual analysis can be tracked automatically. Long-term atmospheric trends become easier to detect. Rare events stand out more clearly against decades of accumulated observations. These techniques do not replace traditional physics. They strengthen it. Laboratory research has progressed as well. Although no laboratory can recreate an entire planet, researchers increasingly reproduce tiny portions of Neptune's interior under controlled conditions. Powerful lasers briefly generate pressures comparable to those thousands of kilometers beneath Neptune's clouds. Diamond anvil cells compress microscopic samples to extraordinary densities. These experiments help determine how water, methane, ammonia, and hydrogen behave under conditions impossible to experience naturally on Earth. Many long-standing theoretical predictions can now be tested directly. Some have been confirmed. Others require revision. The dialogue between theory and experiment continues. Yet despite all these advances, one limitation remains impossible to overcome from Earth. No telescope can measure Neptune's gravity field with the precision of an orbiting spacecraft. No observatory can sample atmospheric gases directly. No Earth-based instrument can descend through the clouds measuring temperature, pressure, and composition as it falls. Some questions require proximity. Others require touch. Modern astronomy has therefore reached an interesting stage. Observations have become increasingly sophisticated. Models have become increasingly realistic. Laboratory experiments have become increasingly powerful. Together they have transformed our understanding of Neptune, and yet many of the most important mysteries remain unresolved. Perhaps this should not surprise us. Each generation of scientific instruments has expanded the frontier of knowledge. It has also expanded the frontier of ignorance. Every new answer reveals questions that previous generations never realized they should ask. Neptune has followed this pattern faithfully. The clearer the planet becomes, the more intricate its story appears. Rather than approaching certainty, astronomers increasingly appreciate how much remains unknown. That realization is not discouraging. It is precisely what makes Neptune one of the most compelling worlds in the solar system. For beyond every measurement lies another mystery waiting to be understood. One of the most valuable words in science is a simple one: unknown. Outside scientific research, the word sometimes carries an unfortunate reputation. It can sound like failure, uncertainty, or incomplete understanding. Yet within astronomy, the unknown has a very different meaning. It marks the frontier. Everything beyond that boundary represents an opportunity to learn something that no human being has ever known before. Neptune stands almost entirely along that frontier. Even after centuries of observation and decades of increasingly sophisticated research, many of its most important characteristics remain only partially understood. Consider its atmosphere. Astronomers have measured some of the fastest winds in the solar system, tracked enormous storms, identified methane clouds, and monitored seasonal changes across decades. Yet one basic question remains unanswered. Exactly how deep do those winds extend? On Earth, weather occupies only a remarkably thin shell surrounding the planet. Most clouds form within the troposphere, extending roughly 10 to 15 kilometers above the surface. Even the tallest thunderstorms reach only a tiny fraction of Earth's diameter. Neptune offers no such simplicity. Its atmosphere gradually merges with its interior. There is no clear boundary where weather ends and the planet begins. Do the powerful jet streams extend only a few hundred kilometers beneath the visible clouds, or do they penetrate thousands of kilometers downward into the deeper interior? The answer matters enormously. Shallow winds suggest that atmospheric processes dominate. Deep winds imply that the hidden interior directly shapes the entire atmosphere. Recent studies of Jupiter and Saturn have shown that their powerful Jet streams extend much deeper than scientists once believed, reaching thousands of kilometers below the cloud tops before gradually fading. Whether Neptune behaves similarly remains uncertain. Without an orbiting spacecraft capable of making extremely precise gravity measurements, the question cannot yet be answered definitively. Another mystery concerns the atmosphere's chemistry. Methane explains much of Neptune's appearance, but not all of it. Scientists increasingly suspect that complex photochemical reactions occur high in the atmosphere, as ultraviolet sunlight slowly breaks apart methane molecules. The fragments recombine into larger and more complicated hydrocarbons. Some may eventually condense into tiny haze particles suspended throughout the atmosphere. These hazes influence the planet's color, temperature, and cloud formation. Yet their exact composition remains incompletely understood. Even a planet's shade of blue can conceal unanswered physics. The hidden interior presents still greater uncertainties. Models indicate enormous layers of water, ammonia, and methane compressed into unfamiliar states of matter. Some predict extensive regions of superionic water. Others suggest gradual transitions rather than sharply defined layers. Still others indicate complicated mixtures whose behavior has not yet been fully reproduced in laboratories. Every improvement in high-pressure physics changes the picture slightly. Each experiment narrows the possibilities. None has yet provided complete description. The magnetic field raises similar questions. Voyager 2 measured its remarkable geometry during a brief flyby. From those observations, scientists reconstructed the broad structure of Neptune's magnetosphere. But magnetic fields evolve. Earth's magnetic field changes continuously. Jupiter's varies as well. Neptune has not been observed closely enough over long periods to determine whether comparable changes occur there. Does its magnetic field drift gradually over decades? Does the internal dynamo fluctuate? Could entirely new behaviors emerge with longer observations? For now, no one knows. Then there are the storms. Perhaps no feature illustrates Neptune's unpredictability more clearly. Dark vortices appear unexpectedly. Some grow rapidly. Others vanish without obvious explanation. Bright methane clouds form around their edges before dispersing. New storms sometimes emerge in locations where none previously existed. The atmosphere behaves almost like a living system, continually reorganizing itself. Computer models reproduce many aspects of these vortices. None yet captures every observed detail. This reminds us that weather remains difficult to predict even on Earth. On Neptune, where observations are far fewer and direct measurements almost non-existent, the challenge becomes vastly greater. Triton introduces another collection of mysteries. Voyager observed active nitrogen geysers during its flyby. Have they remained active ever since? Do they become stronger during certain seasons? Are entirely new regions now erupting? No spacecraft has returned to find out. The Moon's thin atmosphere also changes with the seasons as nitrogen ice slowly sublimates and refreezes. Because Neptune's seasons last decades, these changes unfold with extraordinary slowness. Human observers witness only tiny portions of the complete cycle. Perhaps the greatest unknown concerns Neptune's past. We know the planet formed more than 4.5 billion years ago. We know Triton was almost certainly captured, but many details remain uncertain. Where exactly did Neptune form? Did it originate closer to the Sun before migrating outward? Did giant planets exchange positions during the chaotic early history of the solar system? Modern models, such as the Nice model, suggest that the outer planets may have experienced substantial orbital rearrangement early in their evolution. If so, Neptune's present orbit may not be the one in which it formed. Its entire history could have unfolded differently from what 19th century astronomers once imagined. Evidence supports portions of these migration models. Other aspects remain under active investigation. Again, certainty gives way to probability. There is also the broader question of comparison. Why are Uranus and Neptune so different? The two planets appear almost like twins. Yet Neptune radiates far more internal heat. Its atmosphere is dramatically more active. Its storms appear stronger. Its winds are faster. Their similarities make their differences even more striking. Perhaps the explanation lies in ancient collisions, perhaps in composition, perhaps in interior structure, or perhaps in processes not yet fully appreciated. At present, no single explanation satisfies every observation. That is why planetary scientists continue studying both worlds together rather than separately. Sometimes the most illuminating mystery is not why one object behaves as it does. It is why two seemingly similar objects behave so differently. This pattern appears throughout astronomy. Binary stars evolve differently despite similar beginnings. Nearby galaxies follow separate histories. Even planets formed within the same stellar system can become remarkably distinct. Nature delights in variation. Finally, there remains a philosophical uncertainty. How representative is Neptune? Does it typify the countless Neptune-sized planets now being discovered around other stars? Or is it in important ways unusual? Without studying many more ice giants, we cannot yet know. Every exoplanet observation provides another clue. Every new atmospheric spectrum broadens the comparison. Yet Neptune remains our nearest example. The irony is almost poetic. The farther astronomers look into the galaxy, the more important this distant blue world becomes. Its mysteries no longer belong only to our solar system. They belong to planetary science as a whole. And every unanswered question quietly points toward the same conclusion. If we truly wish to understand Neptune eventually, we will have to return. There are some places in the solar system that invite repeated visits. Mars lies relatively close to Earth. Launch opportunities occur every 26 months, allowing a steady succession of orbiters, landers, and rovers to build upon one another's discoveries. Even the giant planets Jupiter and Saturn, though vastly farther away, have hosted ambitious missions that remained in orbit for years, transforming our understanding of their complex systems. Neptune is different. It is not merely distant, it is difficult. The average distance between Earth and Neptune is about 4.5 billion kilometers, though the exact separation changes as both planets move around the Sun. Even travelling along carefully planned trajectories, a spacecraft requires well over a decade to arrive. Voyager 2 reached Neptune in approximately 12 years using gravity-assist flybys of Jupiter and Saturn to gain speed. That remains one of the greatest journeys ever undertaken by a robotic spacecraft. The distance alone presents formidable challenges. Radio signals require more than 4 hours to travel one way between Earth and Neptune when the planets are near their average separation. A simple exchange of information becomes an exercise in patience. A command transmitted from Earth cannot be corrected immediately if something unexpected occurs. By the time engineers receive confirmation that the command succeeded, more than 8 hours may have passed. Any spacecraft operating there must possess a remarkable degree of autonomy. Power presents another obstacle. Near-Earth spacecraft often rely on large solar panels. Around Neptune, sunlight has weakened to less than 1% of its intensity at Earth's orbit. Solar arrays capable of producing useful electrical power would need to be extraordinarily large and far less efficient than those operating closer to the Sun. Instead, missions to the outer solar system generally depend on radioisotope power systems. These devices generate electricity from the heat released during the natural radioactive decay of specific isotopes. Unlike solar panels, they function regardless of distance from the Sun. They also provide dependable power for decades, making them particularly valuable for long-duration exploration. Yet such power sources are limited in number and require careful planning. Every proposed outer solar system mission must compete for these valuable resources. Travel time introduces another difficulty. A mission launched today might not reach Neptune for 15 years or more, depending on launch opportunities, propulsion technology, and the planetary alignment needed for gravity assists. By the time scientific data begin arriving, many of the researchers who originally designed the mission may have retired. Some may no longer be alive. Exploring Neptune therefore requires an unusual kind of scientific patience. It becomes an intergenerational endeavour. One group conceives the mission, another builds it, a third analyses the results. Despite these challenges, interest in returning to Neptune has steadily grown. The reason is simple. Voyager 2 answered enough questions to reveal how many remained unanswered. A brief flyby can only accomplish so much. An orbiter would transform the science entirely. Imagine a spacecraft spending years rather than hours studying Neptune. Instead of a single snapshot, it could observe complete life cycles of storms. Instead of one measurement of the magnetic field, it could monitor changes over time. Instead of a fleeting glimpse of Triton, it could repeatedly map the moon's surface, watching for seasonal evolution or fresh geological activity. Long-term observation changes the nature of discovery. Patterns invisible during a flyby become unmistakable after years of monitoring. Climate emerges from weather. Evolution emerges from isolated events. Some mission concepts go even further. Planetary scientists have proposed atmospheric probes capable of descending into Neptune's upper atmosphere. Such probes would directly measure temperature, pressure, wind speed, and chemical composition, while transmitting data back to an accompanying orbiter. For the first time, researchers could compare remote observations with direct in situ measurements. This combination proved extraordinarily successful during the exploration of Jupiter. In 1995, the Galileo atmospheric probe entered Jupiter's atmosphere, providing invaluable measurements that could never have been obtained remotely. A similar investigation at Neptune would likely revolutionize our understanding of ice giant atmospheres. The challenge, of course, lies in survival. As a probe descends, pressure rises relentlessly. Temperatures increase. Communication becomes increasingly difficult. Eventually, the environment exceeds the design limits of any foreseeable spacecraft. The probe would almost certainly be destroyed. Its mission would not be to reach a solid surface. Indeed, no such surface exists in the familiar sense. Instead, it would transmit data for as long as possible while sinking deeper into the atmosphere, extending humanity's direct knowledge farther than ever before. Triton represents another compelling destination. Many scientists regard it as one of the highest priority ocean world candidates in the outer solar system. Although its surface temperature is extraordinarily low, internal heat may preserve liquid water beneath its icy crust. If such an ocean exists, Triton joins a remarkable family that includes Jupiter's moon Europa and Saturn's moon Enceladus. Each world demonstrates that liquid water need not exist only within the traditional habitable zone around a star. Heat from tidal interactions and radioactive decay can sustain hidden oceans, even in the frozen darkness beyond Neptune. Whether Triton's interior remains active enough to maintain such an ocean remains uncertain. A future orbiter could provide the measurements needed to answer that question. Beyond the scientific rewards lies another reason for returning: comparison. Planetary science advances most rapidly when similar worlds can be studied together. The success of the Cassini-Huygens transformed our understanding of Saturn precisely because earlier missions had already explored Jupiter. Patterns emerged. Differences became meaningful. The same opportunity now exists for the ice giants. Many researchers argue that understanding Uranus and Neptune together is essential. One orbiter at each planet would provide complementary data sets impossible to obtain from a single destination alone. Together they could explain why two apparently similar planets evolved so differently. For now, however, these remain plans rather than realities. Engineering studies continue. Mission concepts evolve. International collaborations explore possibilities. Each proposal balances scientific ambition against technological limits. Available budgets, launch opportunities, and decades of operational commitment. The questions are no longer whether Neptune deserves another mission. Most planetary scientists agree that it does. The questions concern when such a mission can begin, what instruments it should carry, and which mysteries deserve highest priority. The edge of knowledge often lies not where curiosity ends, but where technology has not yet caught up with it. Neptune occupies exactly that boundary. We know enough to recognize its extraordinary complexity. We do not yet possess the tools to answer every question it raises. Until these tools arrive, Neptune will remain a distant world whose greatest discoveries still wait beneath clouds no spacecraft has ever entered. At the beginning of our journey, hostility seemed like a simple idea. A hostile world was one that would destroy a human visitor quickly. By that measure, the answer appeared obvious. Venus possesses crushing pressure and temperatures capable of melting lead. Mercury experiences blistering days followed by nights colder than many regions of the outer solar system. Jupiter surrounds itself with intense radiation belts that would overwhelm unprotected spacecraft. Even tiny moons scattered throughout the solar system present environments utterly incompatible with human life. Yet the deeper we have travelled into Neptune's story, the more complicated the world has become. Hostility is not merely a matter of temperature. nor is it simply pressure, nor distance. Neptune is hostile because almost every physical process occurring there exists at an extreme beyond ordinary experience. It is a world where the atmosphere never truly rests, where winds race across an endless ocean of gas at astonishing speeds, where pressures increase without any solid ground to interrupt their descent, where chemistry transforms familiar substances into exotic forms, where magnetic fields twist through space in unexpected ways, where a captured moon has reshaped the entire planetary system. Every layer reveals another challenge. If a spacecraft could somehow float within Neptune's upper atmosphere, it would immediately encounter conditions unlike anything on Earth. The air would not be breathable. Hydrogen and helium dominate the atmosphere, accompanied by methane and trace gases. Temperatures in the upper cloud layers approach negative 200 degrees Celsius. Methane ice crystals drift through the air, reflecting what little sunlight reaches the distant planet. Yet even these upper regions represent only the gentlest part of Neptune. As the spacecraft descended, the atmosphere would steadily become denser. Pressure would rise, temperatures would climb. The graceful clouds seen from orbit would give way to increasingly opaque layers where familiar distinctions between atmosphere and interior begin to disappear. Unlike entering Earth's oceans, there would be no coastline announcing a transition, only continuous change. The deeper one travelled, the less meaningful the word sky would become. Eventually, the atmosphere itself would behave more like a dense fluid than a gas. Further still, water, ammonia, methane, and hydrogen would exist under conditions that laboratory experiments reproduce only for tiny fractions of a second. No spacecraft ever built has approached such an environment. Hostility in this sense becomes cumulative. Each additional kilometre downward introduces new physical extremes. Every solution to one challenge reveals another. This layered hostility extends far beyond engineering. It also reshapes our scientific understanding of planetary evolution. For many years, planets were often described using broad categories: rocky planets, gas giants, ice giants. These classifications remain useful, but Neptune demonstrates that each category contains astonishing internal diversity. Jupiter and Saturn are both gas giants, yet Saturn's rings' internal structure and heat transport differ significantly from Jupiter's. Likewise, Uranus and Neptune share the label of ice giant while displaying remarkably different behaviour. Neptune teaches us that planets belonging to the same family may nevertheless follow very different evolutionary paths. That lesson reaches beyond our own solar system. As astronomers discover more Neptune-sized exoplanets, they increasingly recognise that size alone reveals surprisingly little. Two planets of identical mass may possess dramatically different atmospheres. Their magnetic fields may differ. Their internal heat may evolve differently. Their histories of migration and collision may leave lasting signatures invisible from simple measurements of size and orbit. In this way, Neptune has quietly transformed planetary science. Rather than serving merely as another example within an existing category, it has become a reminder that planetary diversity extends far deeper than outward appearance. There is another subtler implication. Neptune demonstrates the remarkable persistence of energy. The planet formed more than 4.5 billion years ago. The solar system itself is ancient beyond ordinary human comprehension, and yet Neptune continues releasing internal heat generated during those earlier stages of planetary formation. That energy has not vanished. It has simply taken billions of years to emerge. This timescale changes the way we think about planetary interiors. A planet does not merely inherit its characteristics at birth. It carries its history forward through immense spans of time. Ancient events continue shaping present conditions. The atmosphere reflects processes occurring deep below. The magnetic field reflects motions hidden within the interior. The rings preserve echoes of past collisions. Triton's orbit records an ancient capture. Every visible feature becomes part of a much longer narrative. Hostility, therefore, becomes historical as well as physical. The conditions observed today cannot be understood without reconstructing billions of years of evolution. Perhaps that is Neptune's greatest gift to planetary science. It encourages us to think in terms of processes rather than objects. Instead of asking what Neptune is, we begin asking what Neptune is becoming. The distinction is subtle, yet it changes everything. A static planet merely exists. An evolving planet tells a story. The same perspective now shapes research across astronomy. Stars are no longer viewed simply as luminous spheres. They are evolving systems. Galaxies are not fixed collections of stars. They grow, merge, and transform. Even the universe itself evolves. Expansion changes the large-scale structure of space across billions of years. Neptune belongs naturally within this broader picture. Its atmosphere evolves. Its interior cools. Its moon slowly spirals inward. Its storms form and disappear. Its climate changes over seasons longer than human civilizations. Nothing remains entirely still. Even at the frozen frontier of the solar system, time continues its quiet work. This realization also carries a measure of humility. For centuries, humanity viewed the outer planets as distant, almost decorative members of the solar system. Modern exploration has revealed something richer. These worlds are not passive ornaments circling the sun. They are active laboratories where physics unfolds under conditions unavailable anywhere else nearby. The hostile environment that once seemed merely forbidding has become scientifically invaluable. Every extreme pressure reveals new states of matter. Every unusual magnetic field tests planetary dynamo theory. Every unexpected storm challenges atmospheric models. Hostility and knowledge become strangely intertwined. The very conditions preventing direct exploration are the same conditions offering profound insight into how planets work. In that sense, Neptune's remoteness has not diminished its importance. It has enhanced it. For here at the cold edge of the sun's domain, one blue world quietly reminds us that nature's most valuable lessons often emerge from places least accessible to us. And if Neptune has continued changing for billions of years already, another question naturally follows. What will become of this restless giant over the billions of years still to come? Looking far into the future requires a different kind of scientific thinking. When astronomers describe tomorrow's weather on Earth, they rely on direct measurements, well-tested physical laws and observations collected continuously from satellites, oceans, and weather stations. The farther into the future they attempt to look, however, the less certain those predictions become. The same principle applies on a much grander scale. Predicting Neptune's future means following physical processes that unfold not over days or centuries, but over billions of years. Some of these processes are understood with considerable confidence. Others remain informed possibilities rather than established outcomes. It is important to distinguish between the two. Certain changes are already underway. Every second Neptune radiates energy into the darkness of space. The amount is modest compared with the energy produced by the sun, yet over immense spans of time, the cumulative effect becomes significant. The planet is slowly cooling. This is not speculation. It is an unavoidable consequence of thermodynamics. Every world that possesses internal heat gradually loses it unless some new energy source replaces what has escaped. Earth is cooling. Jupiter's cooling. Neptune is cooling as well. The remarkable feature is not that cooling occurs, it is how slowly it happens. Neptune's enormous size gives it tremendous thermal inertia. The deep interior stores vast quantities of energy accumulated during planetary formation. Thousands of kilometers of dense material separate that interior from the cold vacuum of space, acting as an extraordinary insulating blanket. As a result, the planet changes almost imperceptibly during a human lifetime. Even over recorded history, its overall structure has remained essentially unchanged. Yet geological time tells a different story. Given enough millions and billions of years, the internal reservoir of heat must gradually diminish. If Neptune's present atmospheric activity depends primarily upon that escaping heat, then its weather should slowly evolve as well. The change, however, would almost certainly be subtle. Storms would not suddenly disappear. The atmosphere would not abruptly become still. Instead, circulation patterns might slowly weaken. Temperature differences could become smaller. Cloud formation might occur somewhat less frequently. These possibilities emerge naturally from current models of planetary evolution. Exactly how rapidly such changes would occur remains uncertain. That uncertainty reflects one of the central themes of our journey. We still do not fully understand how efficiently Neptune transports heat from its interior to its atmosphere. Different models therefore predict somewhat different futures. Another long-term process concerns Triton. Its retrograde orbit guarantees that tidal interactions continue removing orbital energy. Each orbit brings the Moon imperceptibly closer to Neptune. The movement is astonishingly slow. No telescope will detect the change during a single human lifetime. Yet over billions of years, the cumulative effect becomes profound. Eventually, Triton is expected to approach the Roche limit, the distance at which Neptune's tidal forces become stronger than the Moon's own self-gravity. Beyond that boundary, Triton would no longer remain intact. Instead, it would gradually fragment. Countless icy pieces would spread around Neptune, forming an immense ring system. This scenario is strongly supported by the known physics of tidal disruption. The precise timing remains uncertain because it depends upon details of tidal evolution that are still being refined. Nevertheless, the overall outcome is regarded as highly plausible. Ironically, the destruction of Triton would likely create one of the most beautiful planetary systems in the solar system. For a time, Neptune's rings could become vastly brighter and more extensive than the faint structures observed today. Beauty and destruction would become inseparable. Another future depends not on Neptune itself, but on the Sun. Our star is currently middle-aged. Roughly 5 billion years from now, it will exhaust the hydrogen fuel within its core and begin expanding into a red giant. This transformation will dramatically reshape the solar system. Mercury will almost certainly disappear. Venus will almost certainly be engulfed. Earth's ultimate fate remains the subject of continuing research, though it will certainly become uninhabitable long before any possible engulfment. Neptune lies much farther away. Its orbit will expand somewhat as the aging Sun loses mass through powerful stellar winds. The increased distance will alter the planet's path without ejecting it from the solar system. During the Sun's red giant phase, Neptune will receive far more sunlight than it does today. For perhaps the first time in its history, the outer atmosphere could become noticeably warmer. Methane clouds might change. Upper atmospheric chemistry could evolve. Some frozen materials within the Neptunian system would experience conditions unlike any they had previously encountered. Yet even this dramatic transformation has limits. Neptune remains so distant that it will never resemble the present-day Earth. Its deep interior will continue to dominate much of its behavior. Eventually the Sun itself will shed its outer layers, leaving behind a white dwarf. The remaining solar system will enter a long, quiet chapter. Neptune will continue orbiting this compact stellar remnant in deep darkness. The planet will keep cooling. Its internal heat will slowly decline. Whether faint atmospheric circulation persists for trillions of years remains an open question, requiring models that extend far beyond current observational constraints. Here, the distinction between accepted science and informed speculation becomes especially important. Physics allows such calculations. Observations cannot yet test them directly. The uncertainty therefore grows larger the farther we project into the future. Beyond even these timescales lies an almost unimaginable era. Over hundreds of billions of years, gravitational encounters with passing stars may gradually perturb planetary orbits throughout the galaxy. Some planets could eventually be ejected from their stellar systems entirely. Others may survive indefinitely. Whether Neptune remains bound to the remnants of the solar system across such immense spans of time cannot presently be predicted with confidence. The universe itself continues evolving. Galaxies slowly interact. Stars are born and die. Dark energy drives the continued expansion of space. Against this immense backdrop, Neptune's future becomes part of a much larger cosmic story. There is something quietly beautiful about this perspective. A world that once seemed frozen and unchanging reveals itself as another participant in the continual evolution of the universe. Its storms are temporary. Its rings are temporary. Its moons are temporary. Even its orbit will slowly change. Nothing remains fixed forever. And yet throughout these immense transformations, the physical laws governing Neptune remain the same. Gravity continues its patient work. Thermodynamics quietly redistributes energy. Matter responds according to principles established long before the solar system existed. The details evolve. The underlying laws endure. When we return from this distant future to the present, the opening question of our journey begins to look very different. Neptune is hostile not because it is frozen in eternal violence. It is hostile because it is still alive with processes that began billions of years ago and continue shaping the planet today. When we began this journey, Neptune seemed almost self-explanatory. It was the 8th planet from the Sun, distant, cold, and wrapped in a beautiful blue atmosphere. If asked to describe it in only a few words, most people would probably have chosen phrases such as frozen giant outer planet or remote world. Those descriptions are not wrong. They are simply incomplete. The farther we have travelled through Neptune's story, the more each of those familiar ideas has quietly changed. Distance, for example, once seemed to imply silence. It is an understandable assumption. Sunlight fades steadily with increasing distance from the Sun. Beyond Mars, daylight weakens. Beyond Jupiter, it becomes noticeably dimmer. By the time sunlight reaches Neptune, it carries only a tiny fraction of the energy that warms Earth. One might reasonably expect a world approaching stillness. Instead, Neptune has taught us that planetary activity depends on more than the energy arriving from a star. The planet carries a second source of energy within itself. That hidden reservoir accumulated during its formation, and perhaps shaped by billions of years of internal evolution, continues driving weather on a scale almost unimaginable. The atmosphere is not responding only to the Sun. It is responding to the planet itself. That realization changes the meaning of weather. On Earth, we instinctively associate weather with sunlight. The daily cycle of heating and cooling governs much of our experience. Seasons arise because Earth's axis is tilted relative to its orbit. Storms grow from oceans warmed by the Sun. Neptune reminds us that another path is possible. A planet can remain meteorologically alive even beneath a distant Sun, whose warmth has become little more than a faint contribution. Its storms are powered not only from above but from below. Another assumption has also changed. Cold no longer means inactive. The word cold often suggests the absence of movement. We imagine frozen lakes, motionless ice, and landscapes preserved for centuries without change. Yet Neptune demonstrates that temperature alone reveals very little. Its upper atmosphere ranks among the coldest planetary environments in the solar system. Beneath that frozen exterior, however, energy continues flowing upward through immense layers of exotic matter. Extreme cold and remarkable activity coexist. One does not exclude the other. Perhaps the most surprising transformation concerns our idea of simplicity. Before Voyager 2, Neptune was little more than a distant blue disk. Even after its mathematical discovery in the 19th century, it remained largely anonymous compared with Jupiter or Saturn. Modern exploration has revealed a world of extraordinary complexity. Its magnetic field refuses to align neatly with its rotation. Its winds challenge conventional expectations. Its storms appear and disappear over surprisingly short timescales. Its largest moon almost certainly originated elsewhere before becoming permanently captured. Its faint rings preserve evidence of a dynamic history. Its deep interior remains one of planetary science's greatest mysteries. Every layer reveals another. Every answer leads naturally toward another question. This progression reflects something larger than Neptune itself. It reflects the way science advances. Knowledge rarely replaces mystery. Instead, it transforms one mystery into another. The astronomers who first calculated Neptune's existence could not have imagined methane clouds, supersonic water infrared, spectroscopy, adaptive optics, or space telescopes orbiting far above Earth's atmosphere. Each generation inherited questions from the previous one. Each answered some while discovering others. The frontier moved outward. It never disappeared. That pattern continues today. The James Webb Space Telescope observes Neptune with extraordinary sensitivity. Ground-based observatories monitor evolving storms. Laboratory experiments reproduce pressures approaching those within ice giants. Supercomputers simulate atmospheric circulation in unprecedented detail. And still fundamental questions remain. How exactly does Neptune transport heat from its interior? Why is Uranus so much quieter? How deep do the atmospheric winds extend? What processes govern the birth and death of the giant dark vortices? What is the precise structure of the planet's hidden interior? The remarkable thing is not that these questions exist. The remarkable thing is that they are now precise enough to investigate. Scientific progress often means learning how to ask better questions. Neptune has helped astronomers do exactly that. It has also changed our understanding of planets beyond the solar system. When the first exoplanets were discovered, Neptune suddenly became more than a distant member of our own planetary family. It became a nearby representative of one of the most common categories of planets in the galaxy. Every improvement in our understanding of Neptune improves our understanding of countless distant worlds. Its importance has therefore grown rather than diminished. The more exoplanets we discover, the more valuable Neptune becomes. This quiet irony runs throughout astronomy. Sometimes the nearest example is also the most profound. There is another lesson hidden within Neptune's story. Human perception naturally favours what is immediate. We notice the bright planets visible to the naked eye. We remember the worlds visited repeatedly by spacecraft. We become familiar with places where photographs arrive every week. Neptune exists at the opposite extreme. It changes slowly. It lies far away. It receives little attention outside astronomy, and yet patient observation has revealed extraordinary richness. The lesson extends beyond planetary science. Nature often rewards sustained attention. The longer we observe, the more complexity emerges. The same principle applies to stars, galaxies, ecosystems, and even the history of Earth itself. Time reveals patterns invisible to brief observation. Perhaps that is why Neptune feels so different now than it did at the beginning of our journey. The planet itself has not changed. Our perspective has. The blue disk that once appeared simple now carries hidden depth. The cold atmosphere now suggests concealed energy. The distant orbit now speaks of billions of years of evolution. Hostility itself has acquired new meaning. It is no longer merely an obstacle to exploration. It has become evidence. Evidence that the universe continues producing environments more intricate than our first intuitions suggest. And yet, despite everything we have learned, Neptune remains wonderfully unfinished. Its greatest mysteries still lie beneath clouds no human instrument has ever entered. Its hidden interior continues shaping storms that no one can fully explain. Its future awaits observations that have not yet been made. Our understanding has expanded enormously. Our curiosity has expanded even more. There remains only one final step, not another explanation, not another theory. Only a moment of quiet reflection on what this distant blue world has revealed about planets, about science, and perhaps about the universe itself. The farther we travel into the universe, the more often we discover that appearances are gentle disguises. Neptune has remained throughout human history a small blue point suspended near the edge of the sun's domain. To generations of observers, it seemed almost decorative, a quiet conclusion to the family of major planets. Even today, most people will never see it through a telescope. It is simply too distant, too faint, too patient. And perhaps that is why its story feels so remarkable. Nothing about Neptune demands immediate attention. It waits. It circles the sun once every 165 Earth years, moving through seasons that last longer than entire civilizations. Storms larger than our planet are born and disappear while human history unfolds almost unnoticed beneath them. Deep inside, ancient heat continues its slow journey towards space, carrying with it memories of a world that formed when the solar system itself was young. Its clocks run differently from ours. The rhythms of Neptune are measured not in days, but in ages. During this journey, we've encountered winds faster than any found on Earth, invisible magnetic fields shaped by unfamiliar interiors, methane clouds floating through perpetual twilight, and a captured moon whose orbit quietly tells the story of an ancient gravitational encounter. Each discovery answered a question. Each answer opened another. That pattern may be the most enduring lesson of all. Science is often imagined as a collection of completed facts, each one replacing uncertainty with certainty. Yet Neptune reminds us that knowledge rarely works that way. Every improvement in observation enlarges not only what we understand, but also what we recognize remains unexplored. Voyager 2 transformed a distant point of light into a living world. Modern telescopes transformed that living world into an intricate planetary system. Future spacecraft will almost certainly transform it again. Each generation inherits a clearer picture than the last, while also inheriting deeper questions. There is something quietly reassuring about that. The universe has not become smaller because we have learned more. It has become richer. Neptune also reminds us that nature does not organize itself according to human expectations. Distance does not guarantee stillness. Cold does not guarantee silence. Darkness does not guarantee inactivity. Again and again, the planet has overturned assumptions that once seemed perfectly reasonable. Rather than diminishing our confidence in science, these surprises strengthen it. Science is valuable not because it confirms our expectations, but because it gently corrects them. The universe is under no obligation to resemble our first impressions. Perhaps nowhere is this more evident than in the hidden interior of Neptune. No telescope has ever looked directly into those immense depths. No spacecraft has sampled the layers where pressure transforms ordinary matter into unfamiliar forms. And yet from clouds drifting across the atmosphere, from faint infrared light, from subtle variations in gravity and magnetism, astronomers have reconstructed an increasingly coherent story. It is a reminder that understanding often begins long before direct observation becomes possible. Sometimes the smallest clues carry the greatest meaning: a slight shift in light, a tiny change in an orbit, a cloud moving a little faster than expected. From such delicate evidence, entire worlds emerge. That way of thinking reaches far beyond Neptune. The same methods now allow astronomers to study planets orbiting stars hundreds of light years away. Many of those distant worlds resemble Neptune more closely than they resemble Earth. Their atmospheres, climates, and hidden interiors remain almost entirely beyond direct exploration. Yet each observation brings them a little closer. The lessons learned from one quiet blue planet at the edge of our solar system ripple outward across the galaxy. In that sense, Neptune is both familiar and universal. It is our nearest example of a type of planet that may be extraordinarily common throughout the Milky Way. And still, after all these years, it refuses to surrender every secret. Perhaps that is exactly as it should be. Complete certainty would leave little reason to continue exploring. Curiosity survives because the horizon always remains just beyond reach. Every unanswered question becomes an invitation rather than an obstacle. Somewhere in the decades ahead, another spacecraft may begin the long voyage outward. It may spend years crossing the immense darkness between the giant planets before finally entering Neptune's blue realm. New instruments will examine clouds in greater detail than Voyager ever could. They may descend into the atmosphere orbit. Triton measure the magnetic field over many years, and reveal hidden layers that today exist only within computer models and careful scientific inference. When that day comes, the story will not end. It will simply begin another chapter. For now, Neptune continues its patient orbit beneath a distant sun wrapped in deep blue clouds, carrying ancient warmth through the coldest reaches of the planetary family. It asks nothing of us except time, careful observation, and the willingness to accept that some of the greatest discoveries arrive quietly. We began with a simple belief that the most distant giant planet should be cold, calm, and nearly motionless. We leave with a very different understanding. Neptune is not the silent ending of the solar system. It is one of its most active conversations. And as it continues its slow journey through the darkness, one gentle question remains waiting for the next generation of explorers to answer. If a world so distant can still surprise us after nearly 2 centuries of study, what other quiet mysteries are waiting in the countless blue planets that drift unseen among the stars?